Hello there and welcome to Physics with William, where curiosity gets cosy and science takes the scenic route to slumber. Tonight, we're easing our way into one of the strangest states of matter ever discovered. A liquid so smooth, so unusual, and so deeply quantum that it seems almost rude to call it a liquid at all. It can flow without ordinary friction. It can slip through openings so tiny they seem sealed. It can crawl up the sides of a container and spill itself over the edge, as if it has quietly decided that gravity is more of a suggestion than a rule. This is the world of superfluidity, and if you have never heard of it before, do not worry. It is not the sort of thing that usually comes up while waiting for the kettle to boil, though after tonight you may never look at a cup of tea in quite the same way again. Before we begin, I would love to know where in the world you are listening from tonight, and what is near you as you settle in. Is there a glass of water on your bedside table, a mug of tea cooling slowly nearby, or perhaps nothing at all except the quiet room around you? It is a fitting question for a story about liquid, because most of us meet liquids in the most ordinary places, in cups, sinks, rivers, raindrops, soup bowls, and the occasional unfortunate spill on a clean shirt just before leaving the house. Liquids are familiar. They pour, they splash, they take the shape of whatever holds them, and if they climb up the walls, we usually assume something has gone wrong with the plumbing. But in the deep cold, far colder than any winter night, far colder than the inside of any freezer, one particular liquid begins to behave in a way that feels less like everyday matter and more like a secret message from the quantum world. If you find this kind of gentle science soothing, or if it helps your thoughts slow down at the end of the day, I would be grateful if you gave the video a like and subscribed. It helps this quiet corner of science reach other curious travellers who might also enjoy drifting towards sleep while learning why the universe is far stranger than it first appears. And as always, I do hope this is calming enough to let you rest, but interesting enough to make the edges of your mind glow softly for a little while. So settle in, loosen your shoulders, let the day move a little farther away, and let us begin with a liquid that does something liquids are absolutely not supposed to do. Imagine a small open cup sitting in a laboratory. Inside it is not water, not alcohol, not oil, but helium. Most of the time we know helium as a gas, the light stuff that fills party balloons and makes voices briefly sound like cartoon mice at birthday parties. But if helium is cooled enough, it becomes a liquid. That alone is already unusual because helium is stubborn. It does not easily settle down into a liquid. It has to be chilled to temperatures so low that the word cold begins to feel inadequate. This is not the cold of snow, not the cold of a winter pond, not even the cold of dry ice hissing in a classroom demonstration. It is cold close to the bottom limit of temperature itself, where atoms have almost no thermal motion left to give up, and matter begins to reveal habits that are normally hidden from us. At first, liquid helium seems strange but manageable. It sits in its container, it can be poured, it bubbles and boils in ways that make physicists lean forward with interest. But then, under the right conditions, something changes. The liquid enters a state called a superfluid, and once that happens, the rules of common sense start to feel a little underprepared. A thin film of the liquid spreads along the inside wall of the container. It climbs upward, not in great dramatic waves, but quietly, steadily, in a layer so delicate it can be difficult to see. Then it reaches the rim, then it slips over, then it continues down the outside, as if the cup has failed to explain its boundaries clearly enough. Leave it alone, and the superfluid can slowly empty itself from the container by climbing out. That image is so odd that it deserves a moment. A liquid in a cup climbs the wall, goes over the edge, and leaves. Not because it is boiling away, not because someone tilted the cup, not because of a hidden pump or a tiny experimental prank, although one can sympathise with any tired graduate student who might briefly suspect one. It leaves because in the superfluid state the liquid can flow in a way that ordinary liquids cannot. It is not behaving like water, honey, milk, or even the slipperiest oil. It is behaving like a large-scale quantum object, something whose deepest rules come not from everyday kitchen experience, but from the strange mathematics of atoms moving together as one. For most of us, friction is so ordinary that we barely notice it until it becomes inconvenient. Rub your hands together and they warm up. Slide a chair across the floor and it resists. Stir syrup and the spoon drags. Even water, which feels smooth, has internal friction. It swirls, eddies, slows down, and eventually comes to rest. If you set water spinning in a bowl, it will not spin forever. The motion gradually dies away because energy is lost into tiny internal movements, into heat, into turbulence, into the ordinary messiness of matter. Liquids are full of this hidden resistance. Their molecules bump, tug, drag, and jostle one another. Even when they look smooth to the eye, at the microscopic level there is a great deal of busy negotiation going on. A superfluid is different. In its most famous form, made from helium cooled to extreme temperatures, part of the liquid flows with no ordinary viscosity at all. Viscosity is the thickness or internal resistance of a fluid. Honey has high viscosity. Water has much lower viscosity. A superfluid has, in one sense, none. It can move without the usual drag that slows fluids down. It can pass through tiny channels that would stop ordinary liquids. It can keep flowing around a loop for astonishingly long times, because there is no normal friction to bring it to rest. It is not magic, though it does have the slightly suspicious manners of magic. It is physics, but physics of a kind that asks us to stop thinking of atoms as tiny billiard balls and start thinking of them as waves that can overlap, merge, and act together. That is one of the hardest parts to imagine, because our senses were not built for the quantum world. We evolved to handle falling fruit, flowing rivers, warm fires, sharp stones, hungry animals, and the social danger of forgetting someone's birthday. We did not evolve to intuitively understand what happens when helium atoms are cooled so deeply that their wave-like nature becomes impossible to ignore. At ordinary temperatures, atoms move around with enough energy that their quantum identities stay mostly hidden in the noise. They collide and scatter and behave enough like little particles for everyday language to get by. But at temperatures near absolute cold, their motion becomes calmer. Their wave nature spreads out. Their individual behavior becomes less separate. Under the right conditions, many atoms begin to share a common quantum state, not as a crowd of independent particles each doing its own thing, but as something more coordinated. This is where superfluidity begins to feel both scientific and deeply strange. The liquid becomes able to do things that no ordinary liquid should do, because it is not simply an ordinary liquid with a few unusual features. It is matter reorganized by quantum rules. The small-scale strangeness of atoms has become visible at the human scale. We cannot usually watch quantum mechanics directly with our eyes. We do not see a single atom behave like a wave while making breakfast. But a superfluid is one of those rare phenomena where the quantum world grows large enough to announce itself. It climbs walls. It leaks through near impossible gaps. It flows in ways that seem too smooth for nature. It rotates in tiny whirlpools that obey strict quantum rules. It is as if the universe has allowed one of its hidden backstage mechanisms to wander out under the laboratory lights. And yet, the story does not begin with something dramatic. It begins with cold, careful, patient, technical cold. The kind of cold produced not by weather, but by machines, compressed gases, insulated vessels, and generations of experimental skill. To reach superfluidity, scientists had to learn how to cool helium down to temperatures that no human could survive and no ordinary thermometer could casually describe. They had to learn how matter changes when heat is removed almost completely. They had to build instruments able to detect small differences in flow, pressure, temperature, and motion. Much of this work happened in laboratories where the drama was not in loud explosions or flashing lights, but in subtle readings, quiet persistence, and the occasional moment when a liquid did something so unexpected that the room must have felt briefly less like a workplace and more like a doorway. Think about how familiar liquid water is to us. It can be calm or violent, clear or muddy, shallow or deep. It runs downhill, fills the lowest place it can find, and behaves with a practical honesty that makes it useful for washing dishes and carving canyons. If water climbs a wall, we call it capillary action, or damp, or a problem for the building inspector. It can creep through tiny spaces because molecules cling to surfaces and to one another. But superfluid helium climbing out of a container is not just ordinary wetting behaviour with a colder accent. It is tied to the fact that the liquid can move with almost no resistance. So once a film forms along a surface, it can flow with astonishing ease. The container is no longer a secure boundary in the usual sense. The liquid finds a path and takes it, not with the rush of a spill, but with quiet persistence. There is something almost comic about that. We spend so much effort putting liquids into containers, cups, bottles, pipes, tanks, jars, fuel lines, cooling systems, laboratory flasks. Civilization has a long history of telling liquids where to stay. Then along comes superfluid helium, and under the right conditions it simply climbs out. Very politely, of course. No splash, no tantrum, just a thin, creeping film going about its business. It is the laboratory equivalent of a houseguest who leaves through a window because the front door seemed too conventional. And the more you learn about it, the less it feels like a trick and the more it feels like a lesson. Matter is not obligated to behave in the ways that seem natural to us. Our everyday world is only one temperature range, one pressure range, one scale of experience. Change the conditions enough, and matter reveals entire personalities we would never have guessed. Superfluidity also gives us a gentle warning about the word normal. Normal matter is only normal because we live among it. Water is normal because our bodies are full of it and our planet is shaped by it. Air is normal because we breathe it without thinking. Ice is normal because we have seen it in freezers and on winter roads. But if we lived in a universe where most matter sat near the coldest possible temperatures, perhaps superfluid behaviour would not feel bizarre at all. Perhaps ordinary warm liquids would seem messy, noisy, wasteful, and strangely sluggish. A superfluid is not breaking the laws of physics. It is following them with unusual clarity, in a regime where the usual thermal clutter has been stripped away. It is not nature misbehaving. It is nature behaving in a way we rarely get to witness. This is why superfluidity matters beyond being a beautiful laboratory oddity. It teaches us how quantum mechanics can organize matter on large scales. It connects to superconductivity, where electrical current can flow without ordinary resistance. It offers clues about exotic states inside neutron stars, those dense stellar remnants where matter is squeezed into conditions far beyond anything on Earth. It helps physicists test ideas about vortices, phase transitions, symmetry, and collective behaviour. These may sound like large technical words, and they are, but the heart of the matter is simple enough to hold gently. Sometimes, when many tiny things act together under the right conditions, they produce a new kind of whole. The group does not merely add up. It becomes something with new rules. You can see versions of that idea everywhere, even outside physics. A single bird turns in the air, but a flock can ripple like a living cloud. A single person hums, but a choir can fill a hall with one shared sound. A single water molecule is not wet in the way a puddle is wet. Wetness is something that appears when enough molecules gather and interact. Superfluidity belongs to that family of surprises, though at a much stranger level. It is a collective state. It is many atoms behaving in a coordinated quantum way. The liquid climbs and flows and slips through cracks, not because one atom has decided to be unusual, but because the whole system has entered a state where ordinary friction cannot easily grab hold. There is also a deep calm in the idea of flow without friction. Most things in life seem to lose energy as they move. A spinning top slows, a swing comes to rest. A conversation fades when everyone grows tired. A day winds down whether we are ready or not. We live among resistance. Motion costs something. Effort wears away. So when physics offers a liquid that can flow without that familiar drag, it feels almost restful to imagine. A ring of superfluid current moving on, a liquid finding its way through a narrow space without scraping itself into stillness. Not an escape from reality, but a different version of it, one that exists only under extreme conditions, but still belongs to the same universe as your bedside glass of water. Of course, the liquid that climbs walls is not something we can scoop up in the kitchen or pour into a bedtime mug. Helium becomes superfluid only when cooled to extraordinary temperatures, and it must be handled with great care. It is not a toy liquid, not a curiosity to casually bring home, and definitely not something to test in a teacup, no matter how persuasive an internet comment section may become. The experiments belong in laboratories with proper equipment and trained people, because extreme cold is dangerous in ways that do not always look dramatic at first. But as a phenomenon to think about, it is wonderfully accessible. We can picture the cup, we can picture the liquid, we can picture the strange creeping film, and then we can let that image open a door to the coldest places physics can reach. The first time people encountered this behaviour, it must have been deeply unsettling. Scientists are trained to expect surprises, but they are also trained to measure carefully enough that surprises cannot easily hide. When liquid helium began behaving in ways that did not fit ordinary fluid mechanics, it was not enough to say that it was strange and leave it there. They had to ask what had changed. Why did the liquid suddenly conduct heat so well? Why did it flow so easily? Why did it appear to have more than one kind of motion inside it? Why did it form films that crept along surfaces? Why did rotation behave in discrete little whirlpools instead of ordinary swirling chaos? Each answer led deeper into quantum physics, and each new experiment sharpened the picture. This is one of the pleasures of science when approached slowly. A strange observation is not the end of understanding. It is the beginning of a trail. The liquid climbs out of the container, and instead of shrugging, someone asks why. The flow refuses to slow down, and someone builds a better instrument. The theory seems impossible, and someone finds a way to test it. Little by little, the impossible becomes organised. Not ordinary exactly, but understandable. Superfluidity remains strange even after you explain it, which is perhaps the best kind of scientific wonder. The explanation does not flatten the mystery, it gives the mystery structure. So tonight, we are not rushing toward the hardest details. We're going to take the scenic route, because superfluidity deserves patience. We will begin with cold itself, because cold is not just the absence of warmth in this story, it is the doorway. As temperature falls, matter changes its behaviour. Gases become liquids, liquids become solids, but helium refuses to follow the simplest version of that path. It remains liquid under conditions where many substances would lock into crystal. And then, at a particular depth of cold, it crosses into the superfluid state, where the familiar ideas of thickness, drag, and containment begin to loosen. For now, keep the image simple: a quiet laboratory, a vessel holding liquid helium, a surface that looks still, but is not behaving like any ordinary liquid surface. A film too thin to notice at first, moving along the wall, a liquid that does not splash out but climbs out, a material so cold that atoms begin to act less like separate grains and more like a shared quantum body. This is not a fantasy substance from a story, it is real. It has been measured, studied, argued over, refined into theory, and used as one of the most beautiful examples of quantum mechanics made visible. And to understand how a liquid can become that strange, we need to move gradually downward into the cold, past the temperatures of weather, past the temperatures of ice, past the ordinary world of freezing and melting, until cold itself becomes a kind of laboratory where matter quietly changes its mind. Before a liquid can climb the walls of its container, before it can flow without the usual drag, before it can behave as though it has quietly read a different rulebook from every other fluid on Earth, it first has to enter a place most of us never visit directly. It has to go into the deep cold. Not cold as in stepping outside without a scarf, not cold as in frost on the grass, or a frozen pond, or the little cloud of breath that appears in winter when you say something deeply unnecessary like, well, it is cold today. This is cold far beyond weather. It is cold beyond freezers, beyond ice, beyond the temperatures where most familiar substances have already stiffened, cracked, or settled into stillness. It is cold so extreme that the atoms themselves begin to run out of ordinary ways to move. That is where the story becomes interesting, because cold is not just a lower number on a thermometer. Cold is a change in motion. At the microscopic level, warmth is not a glowing substance hidden inside things. It is movement. It is atoms and molecules jiggling, twisting, vibrating, bumping, and rushing about in their own tiny, restless ways. A hot cup of tea is full of water molecules moving energetically. A cold glass of water has molecules moving more slowly. Ice has molecules locked into a solid structure, though even there they still tremble in place. Nothing in ordinary matter is ever completely still. The smaller you look, the more the world seems to be quietly shivering. So when physicists cool something down, they are not pouring cold into it in the way one might pour milk into tea. They are removing energy. They're taking away some of that hidden motion. The atoms slow, the wildness fades, the substance changes character. A gas may become a liquid may become a solid may become brittle, glassy, or electrically strange. Cooling is a way of persuading matter to reveal what it does when all the thermal noise begins to quiet down. It's like asking a room full of people to stop talking one by one until, at last, you can hear the faint ticking of a watch on the far side of the room. Most of the time, this story feels familiar. Water vapor cools and condenses into droplets. Water cools further and freezes into ice. Wax hardens. Butter stiffens. Metal contracts. We know these changes so well that they seem almost obvious. But helium is not fond of being obvious. Helium is one of the lightest and simplest atoms in the universe, and it has a personality that, from a physicist's point of view, is both elegant and mildly exasperating. It is chemically quiet, refusing to react with much of anything. It is extremely light. It is difficult to liquefy, and once liquefied, it does not behave like a liquid should if your expectations were formed by soup, rainwater, and spilled coffee. To understand why helium matters so much in this story, we need to remember what helium is like before it becomes liquid. In everyday life, helium is a gas. It fills balloons. It escapes easily. It rises through air because it is lighter than the mixture of gases around us. It is the element that gives party balloons their floating charm and gives people a temporary squeaky voice when inhaled. Although that party trick is not as harmless as it is sometimes treated, and the universe would prefer we appreciate helium without treating our lungs like experimental musical instruments. Helium is also produced in stars, including through nuclear processes that have been going on since the early universe. It is ancient, simple, and surprisingly difficult to tame. For a long time, helium resisted liquefaction. Scientists had cooled many gases into liquids, but helium stayed gaseous at temperatures where almost everything else had already given in. The reason has to do with how weakly helium atoms attract one another. They are small, light, and not very interested in clinging together. To make them settle into a liquid, you have to remove an extraordinary amount of thermal motion. You have to cool helium down close to absolute zero, the lowest temperature limit allowed by physics. Absolute zero is not a place you can reach by leaving something outside overnight, no matter how dramatic the winter. It is a theoretical lower boundary, the point where a system has as little thermal energy as it can have. We can come close, very close, but never quite arrive as though stepping through a door. The scale often used for such extreme cold is the Kelvin scale, which begins at absolute zero. On this scale, water freezes not at zero, but at a temperature far above the bottom. That can feel odd at first, because most of us learned temperature through daily life, where 0 might mean freezing or a cold morning depending on which scale you grew up using. But physicists like Kelvin for deep cold, because it starts at the true lower limit. It is a scale built not around human comfort, but around the physical motion of matter. And down near just a few Kelvin above absolute 0, helium finally becomes liquid. That achievement was not a small matter. It took careful engineering, patience, and a great deal of experimental discipline. The Dutch physicist Heike Kamerlingh-Onnes was one of the central figures in the story. In the early 20th century, his laboratory became one of the great temples of low-temperature physics. He and his colleagues developed techniques for cooling gases step by step, using one liquefied gas to help cool another, gradually descending the temperature ladder. It was not the kind of science that happens in a flash of inspiration followed by a triumphant clap of thunder. It was a long technical struggle with pumps, pressure, insulation, glassware, and measurements that had to be taken with exquisite care. Deep cold does not arrive casually, it has to be coaxed. When helium was finally liquefied, it opened a new world. Suddenly scientists had access to a substance that could stay liquid at temperatures where ordinary intuition had very little to say. Most substances, if cooled enough, become solids. Their atoms settle into fixed arrangements. Their motion becomes restricted. But helium is too light and too quantum to freeze under ordinary pressure, even extremely close to absolute 0. This is one of its strangest traits. Even when chilled to depths where most matter would be rigid, helium remains liquid unless pressure is applied. It refuses to settle into a normal solid because the atoms still have a kind of residual quantum motion. They cannot be pinned down into stillness in the simple way one might imagine. This is an important point because it hints at the larger story. At ordinary temperatures, quantum mechanics is always there, but it usually hides beneath the bustle of thermal motion. The atoms are moving so energetically that their wave-like properties are not obvious in everyday behaviour. But as a substance cools, that bustle fades. The quantum character of matter becomes harder to ignore. In helium, because the atoms are so light and the forces between them are so weak, those quantum effects become especially strong. It is almost as if helium is a shy messenger from the quantum world, but only speaks clearly when everything else has grown quiet. The cold needed for superfluidity is therefore not just a dramatic background, it is the condition that allows the phenomenon to exist. At higher temperatures, liquid helium behaves strangely enough, but still in ways that can be described more like an ordinary liquid. It has viscosity, it boils, it carries heat, it flows. But as the temperature drops below a particular point, it changes suddenly. The liquid enters a new phase. This transition is not like water freezing into ice, where you can see a solid structure form. The helium remains liquid. It still looks like a liquid. It still sits in a container, at least at first glance. But its internal behaviour changes profoundly. It becomes a mixture of ordinary fluid behaviour and superfluid behaviour, as though two personalities are occupying the same material. That idea can sound strange, so let's approach it slowly. Imagine a crowd in a station. At a busy time of day, everyone moves in different directions, bumping shoulders, pausing, speeding up, making the whole place seem noisy and complicated. That is somewhat like a warmer liquid, though of course atoms are not commuters and do not stop to buy disappointing sandwiches. Now imagine that, as the station quiets, more and more people begin moving in perfect coordination, not because someone shouts orders, but because the entire crowd somehow settles into one shared motion. Individual wandering fades. Collective behaviour takes over. That is not exactly what happens in helium, but it gives the right flavour. The colder the helium gets, the more its atoms participate in a common quantum state, and the more the superfluid properties dominate. This is one reason superfluidity feels so different from simply making a liquid thinner. When you heat some liquids, they become less viscous. Warm honey pours more easily than cold honey. Warm oil may flow more freely than cold oil, but superfluid helium is not just thin. It is not merely the runniest liquid in the cupboard. It crosses into a state where ordinary viscosity disappears for part of the fluid. That is a completely different kind of behaviour. It is not a gradual improvement in porability. It is a phase transition, a shift in the basic organisation of the material. There is a lovely subtlety here. If you looked at the surface of liquid helium before and after it became superfluid, you might not immediately recognise that anything cosmic had happened. It does not flash. It does not glow. It does not sing. Although one suspects physicists would be delighted if it did. The change is hidden in how it flows, how it conducts heat, how it creeps along surfaces, how it responds to rotation. This is typical of some of the most important discoveries in physics. The universe does not always announce its deepest changes with fireworks. Sometimes it changes the behaviour of a liquid in a glass vessel, and waits for someone patient enough to notice. Deep cold also changes our relationship with time and motion in a practical sense. At room temperature, everything is lively. Thermal energy jostles atoms constantly. Disorder spreads quickly. Any delicate quantum coordination is knocked apart. But cool things down enough, and some kinds of order can survive. This is not order in the everyday sense of a tidy desk, though that would be a welcome side effect of low-temperature physics. It is order in the sense of many particles sharing the same underlying state. It is a form of coordination that emerges only when random motion has been sufficiently reduced. Cold, in this way, is not just emptiness. It is a clearing. It removes the noise so that a quieter kind of physics can appear. This is why the phrase colder than ice does not quite capture it, though it is a useful beginning. Ice is cold to the touch because it draws heat from your skin. It belongs to the human scale of cold. It is familiar, visible, and inconvenient on sidewalks. But superfluid helium belongs to a different landscape entirely. It is colder than ice in the way the deep ocean is wetter than a puddle. Technically true, but not quite enough. At the temperatures where helium becomes superfluid, the ordinary categories of frozen and unfrozen begin to feel incomplete. Here is a liquid that does not freeze under normal pressure, but is colder than almost anything we encounter. Here is matter that remains fluid not because it is warm, but because quantum motion refuses to allow it to lock into a simple crystal. Here is cold producing not stillness but extraordinary motion. That is the first surprise. We often imagine cold as the enemy of movement. Cold makes fingers stiff. Cold makes engines reluctant. Cold makes butter impossible to spread unless one has the patience of a saint or the determination of a person making toast under pressure. But in superfluid helium, cold makes a new kind of movement possible. It strips away the thermal chaos that causes ordinary resistance and allows the fluid to move with uncanny freedom. The colder system is, in one sense, more capable of perfect flow. That is counterintuitive, and it is also beautiful in a very practical way. The universe does not always become simpler when energy is removed. Sometimes it becomes stranger. At this point, it is worth pausing with the image of atoms slowing down. A helium atom in a gas at room temperature is racing about, colliding with other atoms, bouncing off container walls, changing direction constantly. Cool it enough, and the energy of that motion drops. Bring many helium atoms together in the liquid state, and they are close enough to interact, yet still too light and quantum to settle like ordinary matter. Keep cooling, and their wave-like identities begin to overlap in a meaningful way. The liquid is no longer just a crowd of atoms. It begins to behave like a coherent quantum system. That word coherent simply means that the parts are acting in a connected, organised way, rather than as a jumble of separate motions. Coherence is one of those ideas that appears all over physics. A laser beam is coherent light, with waves marching in step rather than jumbling in all directions. A choir singing together produces coherence in sound, at least if everyone knows the tune, and nobody is bravely inventing a new one from the back row. In superfluid helium, coherence appears in the motion of matter itself. The atoms do not become one giant atom exactly, but their collective behaviour is governed by a shared quantum state. That shared behaviour is what allows the liquid to perform its most famous tricks. Still, the tricks come later. First comes the cold, the laboratory discipline, and the strange refusal of helium to freeze. If one were telling the story in a more theatrical way, the cold would be the curtain slowly rising. At ordinary temperatures, helium is a gas. Lower the temperature, and the gas becomes liquid. Lower it further, and the liquid becomes something new while remaining visibly liquid. That is the quiet drama. The appearance changes little, while the underlying rules change enormously. It is a useful reminder that not every important transformation is obvious from the outside. Sometimes the world looks the same until you try to move through it. There is also something humbling about the temperatures involved. Human life exists in a narrow band. Too hot, and proteins unravel, water evaporates, cells fail. Too cold and biological processes slow, tissues freeze, chemistry falters. We are warm creatures, living on a warmish planet, under a warm star. Our intuition is built from that middle range. Low-temperature physics shows us what matter does when removed from the conditions that shaped our senses. It is like listening to a musical instrument played far below the notes we normally hear. The instrument is the same universe, but the tune is unfamiliar. And because it is unfamiliar, the language becomes tricky. We say that heat is removed, atoms slow down, and motion decreases. Then we say the liquid flows without friction, climbs surfaces, and escapes containers. It can sound contradictory, but it is not. The motion that disappears is random thermal motion. The motion that becomes possible is collective quantum flow. A crowd stops milling around randomly, and a coordinated movement becomes possible. The system becomes calmer in one sense and more astonishing in another. That is one of the quiet lessons of superfluidity. Less disorder does not always mean less activity. Sometimes it means a different, more organised kind of activity. The same deep cold that allows helium to become superfluid also led to other great discoveries. In the same broad world of low-temperature physics, scientists found superconductivity, where certain materials allow electric current to move without ordinary electrical resistance. This is not the same phenomenon as superfluidity, but the two are related in spirit. Both reveal what happens when particles coordinate in ways that are hidden at higher temperatures. Both show that resistance, which seems so ordinary in everyday life, is not always inevitable. Under the right conditions, matter can carry motion or current with a kind of persistence that feels almost unreal. The refrigerator, the magnet, the thermometer, the insulated vessel, all become tools for approaching a regime where nature becomes cleaner and stranger at the same time. Liquid helium became especially important because it allowed scientists to reach and maintain those low temperatures. It was not only the subject of the mystery, but also one of the tools for exploring other mysteries. Laboratories used helium to cool materials and instruments, opening the way to discoveries in magnetism, superconductivity, quantum fluids, and eventually technologies that depend on low temperatures. There is a quiet irony in that. Helium is so aloof chemically, so reluctant to interact, and yet it became one of the most useful substances in experimental physics. It does not bond easily, but it helps reveal the bonds of reality. When we speak about superfluid helium, we are usually speaking about a particular form of helium known as helium-4. There is also helium-3, a rarer form that can become superfluid too, but only at even lower temperatures and through a more complicated mechanism. Helium-3 is another extraordinary story, one involving different quantum rules and delicate pairing behaviour, but for now the main path runs through helium-4. It is the classic superfluid, the one most associated with climbing films, frictionless flow, and the great early discoveries. Even there, the full explanation took time to develop. The experimental facts came first. The liquid did strange things. The theory had to catch up. That order is common in science. Nature does not wait for permission from theory. It behaves first. Then people tried to understand. Liquid helium became superfluid whether or not anyone was ready for it. It flowed through narrow gaps. It conducted heat in unexpected ways. It climbed surfaces. It formed strange patterns when rotated. Each observation was like a note slipped under the door. Something different is happening here. The challenge was to read the notes in the right order. For a sleepy science journey, this may seem like a lot of cold, but it matters because the cold is not merely scenery. It is the reason the impossible becomes possible. In a warmer liquid, atoms collide and scatter too much for superfluid coherence to dominate. Any delicate shared quantum behavior is disrupted. In the deep cold, the disruptive motion fades, and the helium atoms can settle into collective behavior. The liquid does not become frozen because helium's quantum motion remains strong enough to prevent ordinary solidification. Instead, it becomes a liquid that is colder than ice, yet freer in its flow than any warm liquid we know. That contrast is the heart of this part of the story. We expect cold things to become rigid. Helium becomes strangely free. We expect liquids to slow and thicken when chilled. Helium becomes capable of motion without ordinary drag. We expect containers to contain. Superfluid helium begins to question that arrangement. Not loudly, not dramatically, just with a thin creeping film that says, in the quietest possible laboratory voice, I have found a way out. It helps to imagine standing near the equipment, not touching anything, of course, because extreme cold is not forgiving. The apparatus is insulated, carefully designed to keep heat from leaking in. There may be glass vessels, metal chambers, valves, pumps, gauges, and the soft seriousness of a room where every connection matters. Inside, helium is being cooled down into a realm where human senses cannot safely follow. At first, it is gas, then liquid. Then, as the temperature drops further, the liquid crosses its remarkable threshold. The surface may look calm, but the physics has changed. If there is a tiny opening, it may find it. If there is a wall, a film may climb it. If there is a loop, flow may persist. Cold has not made the helium dead. It has made it quantum in a way we can see. And perhaps that is why this subject is so compelling for a quiet evening. It begins with something as familiar as liquid and cold, then slowly removes us from the ordinary world without ever fully leaving it. We still have containers, we still have flow, we still have temperature, we still have matter. But each familiar word starts to mean something slightly different. Liquid no longer means ordinary resistance. Cold no longer means frozen stillness. Motion no longer means gradual loss. The same universe that gives us melting ice and dripping taps also gives us helium that slips into a state where the boundary between everyday matter and quantum behavior becomes beautifully thin. So as we move deeper into this story, keep that transition in mind. Superfluidity is not a random trick performed by a strange substance. It is what happens when helium is taken into a cold so deep that the usual noise of matter fades and the hidden rules grow clear. It is the result of a liquid remaining liquid where other substances would freeze, while its atoms enter a shared state that allows extraordinary flow. The wall climbing, the escaping film, the frictionless motion, all of it begins here, in the descent through temperatures colder than ice, colder than winter, colder than almost every natural place on Earth, until helium reaches the quiet threshold where it stops being merely liquid helium and becomes something far more unusual. Helium does not announce itself as a rebel. In ordinary life, it seems almost too light and harmless to be taken seriously. It lifts balloons, escapes through tiny gaps, and gives a party decoration the brief ambition of becoming a weather instrument. It does not burn. It does not rust. It does not easily react with other elements. It is quiet, simple, and aloof. The sort of element that seems to prefer standing at the edge of the chemical dance floor while everyone else forms molecules and makes trouble. But in physics, quiet things often have the deepest secrets. Helium, when cooled far enough, becomes one of the strangest substances ever studied. Not because it is complicated, but because it is so simple that the hidden rules of nature have fewer places to hide. The descent begins with gas. A helium atom is tiny, light, and almost perfectly content to ignore its neighbours. In a balloon, countless helium atoms rush around, bouncing from wall to wall, colliding with one another and with the rubber surface that contains them. They move quickly at room temperature, as all gas atoms do, and their motion creates pressure. That pressure is what keeps the balloon round, at least until helium does what helium does best and sneaks away through openings so small that other gases might politely wait their turn. Helium is famous for escaping. It is not being mischievous, though it certainly gives that impression. Its atoms are small, and their attraction to one another is weak, so they slip through materials with remarkable ease. To turn helium gas into a liquid, scientists have to slow those atoms down dramatically. They must remove heat, lower the temperature, and coax the atoms into staying close enough together to form a liquid. For most gases, this is difficult but not outrageous. Cool oxygen enough, and it becomes a pale blue liquid. Cool nitrogen enough, and it becomes the familiar steaming fluid used in laboratories and cooking demonstrations, usually while someone says, "Please do not touch this," which is excellent advice. But helium resisted scientists for longer than any other gas. It stayed gaseous when others had already condensed. It was like the last guest at a party who refuses to sit down, even after the chairs are clearly available. The reason is that helium atoms barely attract each other. In many substances, atoms or molecules have enough mutual attraction that cooling them allows them to gather into a liquid. Their motion slows, their attractions win, and they settle closer together. Helium's attractions are so weak that even when the atoms slow down enormously, they do not bind easily into an ordinary liquid. To liquefy helium, one must go very near the lowest temperatures possible. The task demanded machines and methods that did not exist until experimental physics had become very good at handling cold. This was not just a matter of putting helium in a freezer and hoping for the best. A household freezer is warm compared with the world helium requires. Even the cold of liquid nitrogen, impressive as it is still too warm for helium to become liquid. Helium waits deeper down. The first great triumph came in the Netherlands, in the laboratory of Heike Kamerlingh-Onnes. His work at Leiden was built around a simple-sounding but enormously difficult goal, to reach temperatures lower than anyone had reached before. This required a careful chain of cooling methods. One gas would be cooled and liquefied, then used to cool another, and so on step by step down the temperature ladder. It was not glamorous in the theatrical sense. It involved pumps, valves, glass vessels, insulation, pressure control, and the patience to solve problems that might leak, crack, clog, freeze, or quietly ruin a day's measurements without even having the decency to make a dramatic noise. Low-temperature physics is often a battle against tiny failures. A little unwanted heat leaks in. A seal is not perfect. A measurement shifts. The experimenter has to notice, adjust, and try again. When helium finally became liquid, it opened a new region of physics. Imagine seeing, for the first time, a substance that had been known only as a gas now sitting as a liquid at the bottom of a carefully cooled vessel. It must have seemed like catching a ghost in a jar, except colder and far more scientifically respectable. Liquid helium was not just another item added to a list, it was a doorway. Its boiling point was so low that it allowed scientists to explore temperatures where metals, magnets, and other materials began doing unexpected things. In fact, the same low-temperature world soon revealed superconductivity, another phenomenon where resistance seems to vanish under special conditions. Helium became not only an object of study, but a key that opened locked rooms in the house of matter. At first, liquid helium was strange enough simply because it remained liquid at such extreme cold. Most substances would freeze solid if cooled sufficiently. Their atoms would settle into fixed patterns, forming crystals. Helium, under ordinary pressure, refuses. Even as the temperature drops closer and closer to absolute zero, helium stays liquid unless it is squeezed under pressure. This is one of the first hints that we are not dealing with a normal substance. It is not that helium is secretly warm, it is that quantum mechanics prevents its atoms from settling completely into a still crystal under those conditions. They retain a kind of restless quantum motion, even when almost all ordinary thermal motion has been removed. This can feel like a contradiction. We often imagine cooling as a path towards stillness. Take away heat, and motion fades. Keep taking it away, and surely the atoms must eventually stop. But atoms are not little beads that can be placed perfectly still on a table. Quantum mechanics does not allow that kind of exact stillness. There is always some unavoidable uncertainty, some basic motion that cannot be drained away like water from a sink. For helium, this matters enormously, because the atoms are so light and their mutual attraction is so weak that unavoidable quantum motion is strong enough to keep them from locking into a solid under normal pressure. It is as if each helium atom is too light and too jittery, in the quantum sense, to agree to sit obediently in a crystal chair. So helium becomes a liquid that should perhaps not exist according to everyday expectations. It is colder than frozen air would be, colder than almost anything familiar, yet it still flows. It is a liquid born not from warmth, but from quantum refusal. And then, as the temperature is lowered further, it does something even stranger. The liquid changes state again. It crosses a threshold where ordinary liquid helium becomes superfluid helium. The transition is subtle to the eye, but profound in behaviour. The liquid does not freeze, it does not become a glassy block or a strange crystal. It remains liquid, but now part of it can move without ordinary viscosity. The impossible has not arrived all at once. It has descended quietly, temperature by temperature, until the liquid has become something that normal language struggles to hold. This transition was first recognized through strange experimental signs. Scientists noticed that liquid helium changed how it carried heat. Below the transition, it became astonishingly good at transporting thermal energy, so good that it seemed to defy ordinary expectations. The surface could stop boiling in the usual way, not because heat was absent, but because the liquid was able to carry heat away with remarkable efficiency. It was as though the helium had learned an entirely new way to handle disturbance. A warmer liquid will bubble and boil when heat enters, forming pockets of vapour that rise and burst. Superfluid helium can respond differently, moving heat with such efficiency that boiling can be suppressed under certain conditions. This was not merely a new measurement, it was a signal that the inner life of the liquid had changed. One famous way of thinking about superfluid helium is that it behaves as though it contains two fluids at once. This does not mean two fluids like oil and vinegar, separating into layers in a bottle of salad dressing. It means the motion of the liquid can be described as having an ordinary component and a superfluid component. The ordinary part behaves more like a familiar fluid, carrying entropy and viscosity. The superfluid part flows without ordinary resistance. These two components occupy the same space, interpenetrating one another in a way that sounds impossible until one remembers that we're in the quantum world now, where common sense often has to remove its shoes at the door and behave humbly. At higher temperatures within the liquid state, the ordinary component dominates. As the temperature drops, the superfluid component grows. Deeper and deeper into the cold, more of the liquid participates in the frictionless quantum flow. This gradual shift helps explain why superfluid helium can show such unusual behaviour while still existing as a liquid. It is not a simple switch from normal to magical, and no physicist would appreciate that word being used as an official term, although late at night it may be tempting. It is a physical transformation in the collective behaviour of atoms. The liquid is reorganizing itself. The deeper the cold, the more the quantum order becomes visible in its motion. This is where helium simplicity becomes powerful. A helium atom is not large or chemically messy. It has no elaborate molecular shape, no complicated bonding behaviour, No internal structure relevant to ordinary chemistry. It is almost a perfect test subject for seeing what quantum mechanics does to matter when the conditions are right. The atoms are bosons in the case of helium-4, which means they can gather into the same quantum state in large numbers. That property is crucial. At very low temperatures, many helium-4 atoms can act in a coordinated way, sharing a common quantum identity that gives rise to the superfluid state. Again, we should be careful not to imagine them as little soldiers marching in rows. They are atoms whose wave-like properties overlap and cooperate. The result is a liquid whose collective motion is governed by rules very different from those of ordinary fluids. A helpful way to imagine this is to think about noise. In a warm liquid, atoms are rushing and scattering in all directions. Their motion is disordered. If some part of the liquid starts to flow, that motion is quickly disrupted by collisions, turbulence, and internal friction. Energy spreads into messy microscopic motion. The flow slows down. In superfluid helium, much of that disruptive thermal motion has been removed. The atoms are not simply quiet, but quantum mechanically coordinated. This makes it difficult for the superfluid component to lose energy in the usual ways. There are restrictions on how it can be disturbed. It cannot simply shed motion into random internal friction, as an ordinary liquid does. The flow becomes unusually persistent. This persistence is one of the most remarkable aspects of the state. If superfluid helium is made to flow in a closed loop, it can keep going for a very long time. An ordinary liquid would slow because friction would convert organized motion into heat. A superfluid can continue because there is no ordinary viscosity in the superfluid component to drain that motion away. It is not perpetual motion in the fantasy sense. It does not create energy from nothing, and it does not violate the laws of thermodynamics. It simply lacks one of the usual mechanisms that would stop the flow. That distinction matters. Physics is full of surprising freedoms, but it rarely hands out loopholes without careful terms and conditions. The quiet descent into the impossible also involved changes in how scientists understood surfaces. In ordinary liquids, surfaces matter, but they rarely seem like escape routes. A liquid wets a container to some degree depending on the attraction between the liquid and the surface. Water beads on wax, spreads on clean glass, and creeps through narrow spaces by capillary action. These are familiar effects, though still fascinating when examined closely. Superfluid helium takes the idea of surface flow further. It forms an extremely thin film on the walls of its container, and because that film can flow with almost no resistance, it can climb, pass over the rim, and continue down the outside. The container has not been broken. The liquid has not been pushed. It has simply found that a surface film is a perfectly good path. It is easy to make this sound like the helium is making decisions. Of course it is not. The liquid has no intention, no preference, no tiny committee debating whether to leave the vessel. But personifying it slightly helps because the behaviour is so unlike what we expect. We say it escapes, it creeps, it refuses, it climbs. These are human words for a non-human process. They remind us how strange the behaviour feels from our scale. A cup is supposed to hold a liquid. The rim is supposed to be a boundary. The wall is supposed to be a wall. Superfluid helium, without meaning to, exposes how many of our everyday assumptions are not laws of nature but habits, formed in a warm and friction-filled world. The deeper scientists studied helium, the more it became clear that this was not a single trick, but a whole new class of behaviour. Superfluid helium could pass through tiny pores that normal liquid helium could not pass through as easily. It responded to rotation in a peculiar way. Instead of swirling like an ordinary bucket of water, it formed quantized vortices, tiny whirlpools whose circulation came in fixed steps. It supported unusual waves, including waves of temperature rather than ordinary surface motion. Even heat could move through it in a way that seemed almost like sound. Each phenomenon pointed to the same underlying message. This liquid was not governed by ordinary fluid mechanics alone. It was a macroscopic quantum fluid. Macroscopic is the important word there. Quantum mechanics is usually introduced through things too small to see directly. Electrons, photons, atoms. Tiny particles behaving in ways that make students stare at the page and wonder whether the textbook has personally betrayed them. But superfluid helium lets quantum behavior show up on a visible scale. You can see the liquid. You can measure its flow. You can watch the effects in laboratory apparatus. It is quantum mechanics made large enough to be handled, though not by bare hands, because again, extreme cold is not interested in anyone's confidence. There is something almost gentle about the way helium enters this state. A metal becoming superconducting may be hidden inside wires and magnets. A particle experiment may require huge machines and abstract analysis. But helium's transformation happens in a liquid that still looks calm, clear, and simple. It is as if the universe has chosen a quiet medium for one of its strangest demonstrations. No bright colour change, no sparks, no dramatic cracking sound. Just a fluid that, below a certain cold threshold, becomes capable of impossible-looking motion. The drama is not in appearance, it is in behaviour. This is often true of phase transitions. We're used to the obvious ones, such as ice melting or water boiling. The change is visible, and the categories are familiar. Solid becomes liquid. Liquid becomes gas. But physics contains many less familiar phase transitions, where the appearance may not change much while the underlying order changes dramatically. Magnetism can appear in a material when tiny magnetic moments align. Superconductivity can emerge when electrons pair and move collectively. Superfluidity appears when atoms enter a shared quantum state that changes the fluid's ability to move. A phase is not just about how something looks, it is about how its parts are organised and how the whole responds. Helium's descent into the impossible is therefore a lesson in hidden organisation. At room temperature, helium atoms are scattered as a gas. Cool them, and they become a liquid. Cool them further, and the liquid enters a new quantum phase. Each step depends on reducing thermal motion, but each step reveals something new rather than merely producing less of the same. The gas does not simply become a slower gas, it condenses into a liquid. The liquid does not simply become a colder liquid, it becomes superfluid. Nature has thresholds, and crossing them can change the rules. One might wonder why this does not happen in every liquid if it is so wonderful. Why not superfluid water, superfluid olive oil, or superfluid soup, which would be both scientifically impressive and disastrous for tablecloths? The answer lies in the details of the particles and their interactions. Most substances freeze before they can reach conditions where this kind of superfluid behaviour would occur. Their atoms or molecules lock into solids. Their structures are too heavy, too complex, too strongly interacting in the wrong ways, or too thermally disordered. Helium is special because it remains liquid at extremely low temperatures and because its atoms have the right quantum character. It is the rare substance that stays fluid long enough for quantum coordination to take over. That rarity makes helium precious scientifically. It also reminds us that the universe does not offer every phenomenon under convenient conditions. Some truths are only visible in narrow windows. To see superfluidity, one must create extreme cold. To see stars form, one must look into immense clouds across space. To study the early universe, one must read faint traces in ancient light. Nature has no obligation to place its secrets at room temperature on a desk. Yet when humans learn how to reach the right conditions, even a small flask of liquid helium can reveal principles that apply far beyond the laboratory. The history of this work is full of careful observation. Scientists did not begin with the complete theory in hand. They saw anomalies. The liquid carried heat too well. It flowed too easily. It behaved strangely near surfaces. It responded oddly to rotation. The explanation emerged through experiments and theoretical insight, with many names contributing to the developing picture. Lev Landau, for instance, developed a powerful theory of superfluid helium that helped explain its excitations and two-fluid behaviour. Others studied films, vortices, and flow through narrow channels. The subject grew because the liquid kept offering puzzles, and each puzzle opened a new way of thinking. For a listener drifting near sleep, perhaps the most useful image is not a list of names or measurements, but the quiet lowering of temperature. Picture helium gas, restless and thin, its atoms moving freely. Picture the cooling machinery drawing energy away. The atoms slow, they gather, the gas becomes a liquid, then the cooling continues. The liquid remains liquid, refusing to freeze. The motion becomes less random, less noisy. Quantum behavior rises from background to foreground. The liquid reaches its transition, and something inside its flow changes. It is still helium, still clear, still contained for the moment, but it has crossed into a state where walls are less final, motion is less costly, and the old language of fluids begins to fail. There is no need to make the story more dramatic than it is. The facts are already strange enough. A simple element becomes liquid only near the bottom of the temperature scale. That liquid stays liquid when most matter would freeze. Cool it further and it becomes a superfluid. A superfluid can flow without ordinary viscosity. It can creep as a thin film along surfaces. It can leave a container by climbing over the rim. It can sustain currents for long periods. It is one of the clearest demonstrations that quantum mechanics is not confined to invisible particles and chalkboard arguments. Under the right conditions, quantum mechanics can fill a vessel, wet its walls, and quietly climb out. And perhaps that is the most charming part of helium's journey. It begins as the light gas of balloons and ends as a liquid that seems to have stepped outside ordinary reality. Nothing about its outward simplicity prepares us for its deep behavior. It is not complex like a protein or messy like a living cell. It is almost austere, just atoms, cold, and quantum rules. Yet from that simplicity comes a state of matter that challenges common sense more effectively than many far more complicated systems. Helium descends into cold, and in doing so, it rises into strangeness. As the temperature continues downward and more of the liquid joins the superfluid state, the next question becomes unavoidable. What does it actually mean for a fluid to flow without ordinary friction? Not just to be thin, not just to pour easily, but to move in a way that resists being slowed by the usual mechanisms of matter. To answer that, we have to follow the motion itself, into narrow channels, around loops, through films, and into the strange calm of a current that can keep going long after an ordinary liquid would have settled into stillness. To follow that motion, we have to set aside the ordinary idea that a liquid stops because it gets tired. Of course, liquids do not get tired, though after watching syrup crawl down the side of a bottle, one might understand the confusion. A fluid slows because its motion is gradually broken apart and spread into heat. The smooth movement of the whole becomes the restless movement of the tiny parts. A swirl in water fades because the moving layers rub against one another. A river loses energy to its bed and banks. Cream stirred into coffee makes curling patterns that soften and disappear. Everywhere in familiar fluids, motion has a cost. Start something moving, and unless you keep pushing, it will eventually settle down. That is so normal that we rarely think of it as a law of our everyday world. It is simply what motion does. But superfluid helium asks a very quiet and very serious question. What if, under the right conditions, a liquid could move without that usual internal rubbing? What if the organised motion did not easily break apart into heat? What if you could set a fluid flowing around a closed path, and instead of fading away like water in a stirred bowl, the flow simply continued? Not because it had found a hidden battery, not because it was creating energy from nowhere, not because a tiny invisible pump was working overtime inside the apparatus, although one imagines that would make laboratory maintenance more interesting. It continues because the ordinary mechanism that drains motion away is missing from the superfluid part of the liquid. In that state, the fluid has learned a new kind of flow. The word forever needs a little care here. In physics, forever is often a dramatic visitor who should be offered tea but not allowed to make all the rules. A superfluid current can persist for an extremely long time, far longer than an ordinary fluid current would, because it does not suffer ordinary viscous drag. In a perfect situation, with no disturbances and no way for energy to leak out, the motion would have no simple reason to stop. Real laboratories are not perfect. Containers have surfaces. Temperatures are not exactly zero. Vibrations exist. Tiny disturbances creep in. Still, the persistence of superfluid flow is so unlike ordinary motion that forever becomes an understandable word to reach for. It feels like the liquid has escaped the usual bargain, the one that says motion must gradually be paid for with heat. To see why this matters, imagine stirring a bowl of water. You move the spoon, and the water begins to spin. At first, the surface dips slightly in the middle, the liquid climbs a little along the sides, and everything looks lively. Then you remove the spoon. The water continues for a while, but not for long. The layers of water rub against each other. The water rubs against the bowl. Tiny eddies form and decay. The neat circular motion dissolves into smaller and smaller movements, until all that organised spinning has been converted into the random microscopic motion we call heat. The bowl may not feel warmer in any noticeable way, because the amount is small, but the energy has gone somewhere. It has been scattered into the hidden bustle of the molecules. Now imagine trying the same kind of thought with a superfluid. You have to be careful, because a superfluid cannot be treated exactly like water. It does not simply rotate as a smooth bulk in the ordinary way. Its rotation has quantum rules of its own, which will become important later. But the main point is this. If the superfluid component is made to move through a narrow path or around a loop, it does not experience ordinary viscosity. There is no normal internal friction in that component to grind the motion away. The flow can remain, not for a few seconds, not for the length of a polite pause, but for times so long that the comparison with ordinary fluids becomes almost unfair. Water has no chance in this contest. Honey has already gone home. This is one of the reasons superfluidity changed how physicists thought about fluids. Before superfluids were discovered, viscosity seemed like one of those unavoidable features of real liquids. Different fluids had different amounts of it, certainly. Honey resists a spoon much more than water does. Oil behaves differently from alcohol. Molten glass, if we're allowed to call it a liquid in a very patient mood, moves so slowly that it seems almost solid. But all ordinary fluids have some internal friction. They all lose organised motion. They all turn flow into heat. Superfluid helium showed that viscosity was not an absolute requirement for a liquid. Under certain quantum conditions, a liquid could exist in a state where the superfluid part had none. This is not just a matter of being very slippery. Slippery is still an ordinary word for ordinary surfaces. Ice is slippery because a foot or skate can move across it with reduced friction under certain conditions. Oil makes surfaces slippery because it separates them and reduces rubbing. But a superfluid is not merely a lubricant. It is not just a liquid with an unusually smooth personality. The absence of ordinary viscosity is a property of the fluid state itself. It is built into the collective quantum behaviour of the atoms. The liquid is not simply avoiding friction at a surface. It is missing the ordinary internal drag that makes one layer of fluid resist the motion of another. One way to approach this is to think about what happens when a fluid flows through a pipe. In an ordinary liquid, the layer near the wall is slowed by interaction with the surface. The layer just inside that is slowed by the first layer, and so on. The flow is fastest near the centre and slower near the walls. Energy is lost through this internal shearing. If the liquid is thick, the loss is larger. If the liquid is thin, the loss is smaller, but it is there. Engineers spend whole careers thinking about this, which is admirable, because without them our plumbing would have the confidence of a garden hose tied in a knot. In a superfluid, the superfluid component can move through very narrow channels without that ordinary shearing resistance. There are experiments where liquid helium is placed on one side of a barrier full of tiny pores. The pores are so narrow that the ordinary component of the fluid cannot easily pass, but the superfluid component can. This kind of barrier is often called a super leak, a wonderfully direct name that sounds as if it belongs equally in a laboratory and in a very unfortunate basement. Through such tiny passages, the superfluid flows with remarkable ease. It is not squeezed through by ordinary pressure in quite the same way a normal liquid would be. It moves because its quantum state allows it to pass through the narrow paths without suffering the usual viscous resistance. The idea that part of the fluid can flow while another part behaves differently brings us back to the two-fluid picture. Superfluid helium below its transition temperature can be described as having a normal component and a superfluid component. They are not separated into layers. They occupy the same volume. That may feel odd because everyday mixtures usually sort themselves in visible ways. Cream in coffee swirls, oil floats on water, mud settles. But the two components of helium are not two substances. They are two kinds of motion within the same substance. The normal component carries entropy and behaves with viscosity. The superfluid component carries no entropy and flows without viscosity. Together they explain many of the strange effects seen in experiments. This picture helps make sense of how flow can be so persistent. If the superfluid component is set in motion, it cannot simply slow by the ordinary transfer of energy into random thermal disorder. There are only certain allowed ways for the fluid to be disturbed. At low enough speeds, and in the right conditions, those disturbances are not easily created. The flow is protected, not by a wall or a mechanical lock, but by the structure of the quantum state. It is like trying to spend money in a shop that only accepts coins of a certain kind, while you have none of the right coins. The transaction cannot happen. The flow cannot easily give up its energy in the usual small, messy increments. This protection is not unlimited. If the flow becomes too fast, or if the container geometry encourages disturbances, the superfluid can create excitations. The motion can break down through processes that involve vortices or other disturbances. In plain words, it is not invincible. A superfluid can be disturbed. It can heat. It can leave the perfect regime. It can behave in complicated ways. But below certain limits, it moves with a calm that ordinary fluids never achieve. This is where the phrase flow forever finds its meaning. Not as a cartoon promise of endless motion in all circumstances, but as a statement that the usual reason for stopping is gone. The difference between ordinary flow and superfluid flow is also a difference in how a fluid remembers. An ordinary liquid forgets motion quickly. Stir water, and soon the water no longer carries a visible record of your stirring. The energy is spread into heat. The memory is lost in molecular noise. A superfluid, moving around a closed loop, can retain the motion. Its quantum state holds the flow in a stable pattern. In some experiments, persistent currents have been observed for very long durations, showing that the fluid can maintain organized motion with extraordinary loyalty. It is not conscious memory, of course, but physical memory. The system remains in a state that records the flow. This is one of those moments when the quantum world feels less like a distant theory and more like a practical fact you could point to through a laboratory window. The flow continues. The current persists. The liquid is not obeying the intuition built from taps, rivers, and soup ladles. It is obeying quantum mechanics at a scale large enough to matter. That is why superfluidity is often placed beside superconductivity in the gallery of remarkable low-temperature phenomena. In a superconductor, electric current can flow without ordinary electrical resistance. In a superfluid, mass flow can occur without ordinary viscosity. In both cases, resistance is not merely reduced, it is absent in a specific and astonishing sense. The motion is carried by a collective state that ordinary scattering cannot easily disrupt. The comparison is useful, though not identical. In a normal wire, electrons moving through a metal scatter off imperfections, vibrations, and other electrons. Their organized motion loses energy, and the wire heats. That is electrical resistance. In a superconductor, under the right conditions, electrons cooperate in a quantum state that allows current to move without that ordinary resistance. In a normal liquid, atoms and molecules scatter and rub in ways that turn flow into heat. In a superfluid, the collective quantum state allows flow without ordinary viscosity. Both phenomena tell us something profound. Resistance, which feels so unavoidable in everyday life, can disappear when particles act together in the right quantum way. A quiet bedtime warning, though. This does not mean resistance is optional in the personal sense. We cannot solve a difficult morning by entering a superfluid state, however appealing that may sound. The physical conditions are extreme, and the quantum coordination belongs to particles, not to a sleepy person looking for socks. Still, there is a certain comfort in knowing that the universe contains modes of motion that are smoother than anything our daily experience suggests. Reality has more possibilities than habit teaches us. The moment a fluid learns to flow forever is also the moment we must change our idea of what a fluid is. In school, fluids are often introduced as substances that flow and take the shape of their containers. That is a good start. It covers water, air, oil, and many other familiar materials. But superfluid helium reveals that the word fluid can include behavior far beyond pouring and splashing. A fluid can be a quantum state. It can have a shared wave-like identity. It can respond to motion through rules that have no obvious counterpart in a kitchen sink. A fluid can become so coherent that ordinary friction cannot catch it. Coherence is the key word hiding beneath much of this. In an ordinary liquid, the particles move with a great deal of independence. They interact constantly, but the overall state is not one shared quantum motion. In a superfluid, many atoms participate in a single collective behavior. Because of that, the fluid cannot be treated as a crowd of separate little objects bumping around in a purely classical way. It has to be treated as a quantum whole. This does not mean every atom is doing exactly the same thing in a simple mechanical sense. It means the state of the fluid is coordinated by a common quantum description. That coordination is what makes the flow so unusual. If that still feels difficult, it should. The human mind is comfortable with objects. A stone is here, a cup is there. Water pours from one to the other, but quantum states are not objects in the same everyday way. They are descriptions of possible behavior, wave-like patterns, shared conditions that determine how matter can move and respond. Superfluidity asks us to accept that a visible amount of liquid can be governed by such a state. It is not just that each atom is strange. The whole liquid is strange together. There is a wonderful experiment often associated with this idea of persistent motion. If superfluid helium is placed in a ring-shaped channel and made to flow around the ring, the current can continue. In an ordinary liquid, the ring would be a circular trap only briefly. Friction with the walls and internal viscosity would slow the motion. In the superfluid, the circulation can remain. The liquid goes around and around, not because it has decided to be dramatic, but because nothing in the ordinary viscous sense is draining it away. The ring becomes a quiet demonstration of motion without ordinary loss. Even more surprising, the flow in such systems is not arbitrary. Because the superfluid is governed by quantum mechanics, the circulation can come in discrete amounts. In ordinary water, a whirlpool can have almost any strength depending on how it was formed. In a superfluid, certain kinds of circulation are quantized. That simply means they come in fixed steps. Nature does not allow every possible value. It permits certain patterns and rejects the in-between options. It is a little like a staircase rather than a ramp. You can stand on one step or another, but not halfway between without doing something awkward. This quantization becomes especially important when superfluids rotate and form vortices, and it will lead us towards some of the most visually striking behavior in the subject. For now, though, the main lesson is that the superfluid state makes motion unusually stable. It does not make all motion effortless in every situation. It does not make the liquid immune to disturbance. It does not turn helium into a fantasy substance that solves all engineering problems. But it does show that when matter is cooled into the right quantum condition, flow can persist without ordinary friction. That fact alone is enough to make superfluidity one of the great surprises of 20th century physics. There is also a heat story intertwined with the flow story. Superfluid helium carries heat in ways that seem astonishing. In ordinary materials, heat spreads by conduction, convection, and radiation. In liquids, warmer regions may rise and cooler regions may sink, creating currents. In superfluid helium, the two components can move relative to each other in response to temperature differences, producing extremely efficient heat transport. Under some conditions, a temperature disturbance can travel through the liquid like a wave, not a sound wave of pressure in the usual sense, but a wave of temperature. This is often called second sound. It is one of those terms that sounds modest until you realize what it means. Heat, which we usually expect to diffuse and smear out, can move like a wave through a quantum liquid. That heat behavior is part of why early researchers realized something extraordinary was happening. The liquid was not just thin, it was reorganized. It handled motion and heat in new ways. When heat entered, the response could be swift and collective. When flow began, it could persist. When the liquid encountered narrow passages, part of it could slip through. These were not isolated curiosities. They were symptoms of a new state of matter. It is important to keep the state of matter idea close. Superfluidity is not a single property like colour or density. It is a phase, a mode of organisation. Water as ice, liquid and vapour is still water, but its behaviour changes because the molecules are arranged and moving differently. Helium as a normal liquid and helium as a superfluid is still helium, but its quantum organisation changes. At the transition, the substance enters a new way of being liquid. The atoms have not become another element. They have joined a collective state with new rules for motion. This is why the moment a fluid learns to flow forever is not a single instant like a switch being flipped in a cartoon laboratory. It is a threshold crossed as the temperature falls. Above the threshold, liquid helium is strange but not superfluid. Below it, the superfluid component appears. As the cooling continues, that component becomes more dominant. The liquid becomes more deeply superfluid. The flow becomes more purely governed by quantum behaviour. The descent into cold and the emergence of frictionless motion are tied together. One might ask how scientists know that the flow truly lacks ordinary viscosity. After all, no experiment is perfect, and measuring nothing is often harder than measuring something. The answer is that many different experiments point to the same conclusion. Flow through tiny channels, persistent currents, heat transport, rotational behaviour, and the response of objects moving through the liquid all reveal behaviour that cannot be explained by ordinary viscosity. It is not one surprising measurement standing alone. It is a whole pattern of evidence. The liquid behaves as though a part of it flows without viscous resistance, and the theory built around that idea explains a wide range of observations. Still, there is a subtle distinction. If you drag an object through superfluid helium, the behaviour can depend on speed. Move gently enough, and the object may experience little or no drag from the superfluid component. Move too fast and excitations can appear. The fluid can create disturbances that carry energy away. Then drag returns in a different form. So the superfluid is not a universal friction eraser. It has rules, limits, and thresholds. This is often how nature works. The most beautiful phenomena are not vague miracles. They are precise freedoms with precise boundaries. That precision makes superfluidity even more impressive. It is not just that helium acts weirdly. It acts weirdly in a structured, repeatable, measurable way. It can be studied, predicted, tested. The apparent impossibility becomes a disciplined field of physics. A liquid that flows forever is not a bedtime exaggeration. It is a doorway into understanding collective quantum states, low-temperature matter, and the ways particles can organize themselves into something larger than their individual motions. In a quiet way, this also changes how we think about energy loss. Everyday experience teaches us that smooth motion decays. A bicycle slows if you stop pedaling. A pendulum stops swinging. A spinning coin wobbles and falls. A river current meets rocks and banks. We live in a world where friction is everywhere, so we may confuse common with necessary. Superfluid helium gently corrects us. Friction is not a universal tax on all motion. It is a result of particular interactions under particular conditions. Change the conditions deeply enough, and the tax can vanish. The image of flow without friction can feel almost too clean, especially compared with the ordinary mess of liquids. Anyone who has poured milk too quickly knows that fluids can be chaotic. They splash, foam, drip, spill, and find the one gap in a counter that was not properly wiped. Superfluid helium has its own complications, of course, but the superfluid component moves with a kind of mathematical neatness that ordinary fluids rarely display. Its motion is constrained by quantum rules. Its rotation forms specific structures. Its currents can persist. It is not messy in the usual way. It is strange in a more orderly way. That order is what makes the next behavior possible. If a fluid can flow with almost no resistance, then a thin film of it along a surface can move with surprising ease. If the liquid wets the container wall and forms that film, it does not remain a passive coating. It can carry superfluid flow. It can creep upward. It can pass over the rim. It can continue down the outside. The same absence of ordinary viscosity that allows persistent currents also helps explain why the liquid can seem to escape its container. The wall climbing is not a separate magic trick. It is part of the same story of frictionless motion, surface films, and quantum flow. So the moment a fluid learns to flow forever is also the moment a container begins to lose some of its authority. A wall can still be solid, a rim can still be real, but for a superfluid film the surface itself becomes a path. The liquid does not need to leap, it does not need to splash, it does not need to boil away, it can simply move, steadily and thinly, along the route available to it. What seems like escape is flow, following the rules of a state where ordinary resistance has been removed, and that brings us closer to the most famous image of all. The liquid in the cup, the creeping film, the slow climb up the wall, the quiet spill over the edge. After understanding the cold and the persistent flow, the behaviour is still surprising, but it is no longer random. The superfluid has not become a tiny acrobat. It has become a liquid whose motion is so free that even a film along a surface can carry it away. The next step is to watch that polite rebellion more closely, because when superfluid helium begins climbing walls and escaping cups, it shows us just how far the familiar idea of a liquid can bend without breaking. By now, the liquid has already done the difficult work in secret. It has descended into the deep cold, crossed into its superfluid state, and learned how to move without ordinary viscosity. That is already strange enough. A fluid that can keep flowing without the familiar drag of internal friction is not something everyday experience prepares us for. But then it does something even more unsettling. Not in a dramatic explosion or a theatrical leap, but in the quietest possible way. It climbs. Not like a person climbs, of course. There are no little helium arms reaching up the glass, no tiny mountaineering equipment, no brave atom planting a flag at the rim. It climbs as a film so thin that it can be hard to see, sliding along the wall of a container, moving upward, reaching the lip, passing over, and flowing down the outside. The liquid does not appear to understand that the cup was meant to be the final word on where it should stay. It finds the surface, wets it, and follows it. A polite rebellion, really. No shouting, no splashing. Just a cold, clear liquid quietly leaving the vessel by a route that ordinary liquids would not be able to use in the same way. To appreciate how odd this is, it helps to start with a very ordinary cup of water. Fill a glass and leave it alone. The water sits there. It may evaporate slowly. It may leave a ring or a faint mark where minerals remain. If the glass is narrow, the surface may curve slightly at the edge because of the attraction between water and glass. If you dip a paper towel into it, the water may climb through the fibres by capillary action. But the water does not simply coat the inside of the glass, climb over the rim, and empty itself onto the table as if bored with confinement. If it did, kitchens would be much more stressful places. Water has surface tension, it has viscosity, it interacts with glass. It can creep through very narrow spaces if adhesion and cohesion pull it along, but it loses energy as it moves. Its flow is slowed by internal resistance and by friction with surfaces. A thin film of water on a vertical wall may run downward under gravity or remain trapped in patches depending on the surface, but it does not become an endlessly mobile skin, able to carry the liquid up and out. Gravity and viscosity usually win that argument. With superfluid helium, the argument changes. A superfluid film can form along the walls of its container, because helium wets many surfaces. Wetting simply means the liquid spreads across the surface rather than forming separate droplets. That part is not yet the full miracle. Many ordinary liquids wet surfaces. What makes superfluid helium extraordinary is that once the film forms, it can flow with almost no ordinary resistance. The film becomes a pathway. It is not just a damp coating. It is a moving layer connected to the liquid reservoir below. As long as the conditions allow, the superfluid can travel through that thin layer, climbing the inside wall, crossing the rim, and descending the outside. This is sometimes called film flow, and it is one of the most famous visible signs of superfluidity. The word visible should be used gently, because the film itself is often extremely thin, thinner than a soap film and not always easy to observe directly. But its effects are unmistakable. A container of superfluid helium can slowly lose liquid even when there is no obvious leak in the ordinary sense. The liquid has not cracked the glass. It has not found a hole in the bottom. It has simply used the walls themselves as a road. It is the sort of behaviour that makes a container feel less like a prison and more like a suggestion. There is a subtle balance involved here. Gravity still exists. The helium is not ignoring gravity, and it is certainly not floating upward like a balloon. The film climbs because surface forces and the superfluid ability to flow through the film allow motion along the container wall. Once the film reaches the rim, gravity can help draw it down the outside. The liquid is not violating physics. It is using physics more completely than our everyday instincts expect. When people first hear that a liquid climbs out of a cup, it can sound like a fairy tale. When you slow it down and follow the mechanisms, it becomes even better than a fairy tale, because it is real and still strange. Ordinary fluids can also make thin films, but those films are usually limited by viscosity and by the balance of forces at the surface. If you coat a wall with oil, the oil slowly drains. If you spill water, it spreads and then evaporates or gathers into beads depending on the material. Honey clings to a spoon, but it does not flow upward and escape the jar unless assisted by a very determined breakfast accident. Superfluid helium is different because the film is not just thin, it is superfluid. Its motion is not slowed in the same way. That lets even a tiny layer carry matter over surfaces with remarkable ease. The result can feel almost mischievous. Scientists working with superfluid helium had to learn that containers were not always enough. A vessel open at the top could lose liquid by film creep. A tube, a beaker, or a cooled surface could become part of the path. If the helium could wet it, the helium could move along it. One imagines a laboratory worker carefully checking seals and joints, only to discover that the liquid has been leaving through the most elegant route imaginable, over the rim in a film too thin to scold. It is difficult to be angry at a substance that escapes so politely, but it is also difficult to run an experiment if the subject keeps quietly wandering away. This behaviour is one reason superfluid helium became such a powerful teacher. It showed that the ordinary boundary between inside and outside depends on how matter can move along surfaces. A cup holds water because water cannot easily maintain an upward creeping film that drains the contents under those conditions. The same cup holding superfluid helium at the right temperature is a different story. The The geometry has not changed, the material has. The wall is still solid, but the liquid's relationship with that wall is transformed. In a sense, the container is defeated not by force, but by compatibility. The superfluid finds a path because the surface allows a film, and the film allows flow. There is also an important difference between spilling and escaping. If you knock over a glass of water, the water leaves because gravity pulls it outward after the container is tilted. If superfluid helium creeps out, it leaves while the container remains still. The motion can be slow and continuous, driven by the behavior of the film and the conditions of the fluid. This makes it more unsettling than a spill. A spill is an event. Film creep is a process. It has the quiet persistence of ivy on a wall, except the ivy is a quantum liquid and the wall is inside a cryogenic vessel, which admittedly makes it less suitable for a garden. The phrase climbing walls naturally invites the question of how high the film can go. It does not climb without limit in every circumstance. Real surfaces, temperatures, film thickness, heat flow, and geometry matter. The film has properties of its own, and it can be disrupted, but the ability exists strongly enough that it had to be accounted for in experiments. Superfluid helium does not respect open containers in the way ordinary liquids do. To store and study it, physicists must design apparatus with this creeping film in mind. The laboratory becomes a place where even the walls need to be understood as possible channels. This is one of the recurring lessons of low-temperature physics. At extreme conditions, details that seem minor can become central. A surface is not just a boundary. A tiny opening is not just too small to matter. A thin film is not just a coating. In superfluid helium, small paths can become important because flow is not hindered in the usual way. The liquid takes advantage of routes that ordinary fluids either cannot use or cannot sustain. It is not that the superfluid is more forceful, it is that it wastes less motion. There is another famous polite rebellion that belongs beside wall climbing, and that is the ability of superfluid helium to pass through incredibly tiny holes. In ordinary life, a hole below a certain size becomes an effective barrier. A sieve holds back pasta but lets water through. A coffee filter lets liquid pass while keeping grounds behind, at least when life is going well. A porous plug can restrict flow because the channels are narrow and the fluid loses energy rubbing along their walls. But superfluid helium can pass through fine pores with astonishing ease. At least the superfluid component can. This is the principle behind what physicists call a superleak. A superleak is not simply a bad seal. It is a barrier with openings so small that ordinary viscous flow is strongly suppressed. The normal component of helium, which behaves more like an ordinary fluid, is held back or slowed. The superfluid component passes. The name is wonderfully literal. It lets the super part leak. Through this kind of arrangement, scientists could separate the motions of the two components and explore the two fluid nature of superfluid helium. It was not a separation of two different chemicals, but a way of revealing two kinds of behavior in the same liquid. This is where the wall climbing and the tiny pore flow meet conceptually. In both cases, superfluid helium uses pathways that ordinary fluids cannot use in the same way. A thin surface film becomes a route over the rim. Microscopic pores become channels through a barrier. The common factor is the absence of ordinary viscosity in the superfluid component. When flow does not suffer the usual internal drag, paths that would be impractical or impossible for ordinary fluids become available. That does not mean the liquid can pass through anything. It is not a ghost. A solid wall with no surface route, no connected pores, and no path remains a wall. Superfluid helium does not teleport. It does not dissolve the rules of matter. It follows available paths with extraordinary efficiency. That distinction matters because the real phenomenon is more interesting than a fantasy version. The superfluid is strange precisely because it obeys the laws of physics under conditions that expose hidden possibilities. It does not ignore barriers. It redefines what counts as a useful path. There is a useful everyday comparison in the way water moves through cloth. Dip the edge of a towel into a puddle and water creeps upward through the fibres. That is capillary action, driven by surface forces in narrow spaces. It can look a little like climbing, but if you remove the conditions that sustain it, or if the towel becomes saturated, ordinary limits appear. The water's motion is slowed by viscosity and by the structure of the fibres. Superfluid helium's film flow also involves surface effects, but the superfluid nature of the film makes the motion far more remarkable. It is capillary, like in appearance, quantum in cause, and deeply inconvenient if your experiment assumed that open containers behave themselves. The escaping cup image became famous because it condenses the whole mystery into something almost anyone can picture. A cup, a liquid, a wall, the liquid leaves. That simplicity is powerful. We do not need to begin with abstract quantum states to feel the surprise. We feel it immediately because cups are supposed to work. They are among humanity's oldest technologies. We learn to carry liquids because life depends on it. Bowls, jars, skins, pots, bottles and tanks are all variations on the same idea. Put the liquid in, keep the liquid there. Superfluid helium quietly reveals that this ancient agreement between liquid and container was never universal. It was a local treaty signed under ordinary temperatures. The treaty fails because the liquid has entered a state where collective quantum motion changes what flow means. The helium atoms in the superfluid component are not moving as independent little grains that rub past each other in the usual way. They are part of a shared state. This shared state can extend through the film and along surfaces. The film is thin, but the superfluid order within it can still support motion. So the liquid in the reservoir and the liquid in the film are connected as parts of one coherent system. The surface path is narrow but not useless. The rim is high but not final. There is a small practical detail that makes the phenomenon even more interesting. The film can move in response to differences in the chemical potential of the liquid, which is a technical way of describing the tendency of matter to move from one condition to another. We do not need equations to grasp the point. If the superfluid can lower its overall energy or respond to an imbalance by flowing through the film, it will do so. The film provides the route. Gravity, surface forces, temperature conditions, and the state of the helium all contribute to the final behaviour. The result is not a single simple push upward, but a balance of physical tendencies that together allow the liquid to climb and escape. It is tempting to picture the helium defying gravity, but that is not quite right. Defying gravity would mean gravity has been defeated or switched off. In reality, gravity is part of the story. Once the film crosses the rim, gravity helps pull it down the outside. The climbing portion is made possible by surface interactions and the unusual flow properties of the superfluid film. The liquid is not floating upward through empty air. It is moving along a surface. A wall that seems vertical and restrictive to us becomes a continuous path for the film. In this sense, the superfluid does not break gravity's rule. It finds a loophole in our expectations. The same kind of expectation breaking appears when superfluid helium is placed in nested containers. Imagine a small cup inside a larger vessel. If the small cup holds superfluid helium, a film can climb the inner wall, pass over the rim, and drain into the larger space. It is an almost comically neat escape. The liquid does not need the small cup to be tipped. It simply empties itself through film flow until conditions balance. This is the sort of demonstration that stays in the mind because it feels like a visual riddle. You know the cup was not knocked over. You know the bottom was not punctured. Yet the liquid is no longer where it was. At the same time, one should not imagine this happening at the speed of a waterfall. The film can be slow, the quantities may be small, the behaviour is often delicate. That gentleness is part of the charm. Superfluidity is not always dramatic in the sense of fast motion. It is dramatic because of what the motion means. A slow escape over a wall can be more scientifically shocking than a splash, because a splash tells us nothing new. A creeping superfluid film tells us that the liquid is using a mode of flow outside ordinary experience. There is a quiet laboratory beauty in these effects. The apparatus may be complicated, but the core observation feels simple. The liquid follows surfaces, it passes through tiny paths, it moves without ordinary drag. Each behaviour reinforces the others. If a superfluid can flow indefinitely around a loop, perhaps it is not so surprising that it can also flow through a film. If it can pass a superleak, perhaps a narrow surface layer is not a serious obstacle. If it lacks ordinary viscosity, then the places where viscosity usually matters most, thin channels, small pores, films along walls, become places where its strangeness is most visible. This turns the world of the superfluid into a world of edges and boundaries. Edges are where ordinary matter often reveals its hidden rules. A surface is where liquid meets solid or gas. A pore is where a barrier becomes a passage. A rim is where inside becomes outside. Superfluid helium is especially interesting at these boundaries because it challenges what the boundary can do. A wall may shape it, guide it, or host a film, rather than simply stopping it. The liquid does not erase the boundary. It turns the boundary into part of its root. That idea reaches beyond helium in a quiet way. Many of the strangest things in physics happen when systems meet limits. At very high speeds, time and space behave differently. At very small scales, particles behave like waves. At very low temperatures, matter can become coherent in ways that are hidden at room temperature. At surfaces, in narrow channels, near transitions and under extreme conditions, the universe often reveals that our everyday categories were only approximations. Superfluid helium climbing a wall is one of the gentlest examples of that lesson. It does not require a black hole or a particle collider to surprise us. It only requires a liquid cold enough to let quantum behaviour come to the surface, quite literally. There is also something wonderfully humbling about the role of thinness here. We tend to associate significance with large, visible things. Mountains, oceans, storms, rockets, stars. But the superfluid film is tiny. A layer so thin it can almost vanish from sight becomes the reason a container fails. It is a reminder that nature often works through details too small to notice casually. A thin film can carry a flow. A microscopic pore can reveal a new phase of matter. A subtle change in temperature can transform a liquid's behaviour. The universe is not only strange in grand gestures, it is strange in quiet edges. The wall climbing behaviour also connects to one of the most important themes in superfluidity, the difference between what a substance is and what a substance does. If someone handed you a sealed description saying the sample is liquid helium, that would not tell you enough. At what temperature? Under what pressure? In what geometry? Is it above or below the superfluid transition? Is there a surface film? Are there pores, channels, heat flows, or rotation? Matter is not defined only by its ingredients, it is defined by its state and circumstances. Helium atoms can be a gas in a balloon, a normal liquid in a cryogenic vessel, or a superfluid creeping out of a container. Same element, different world. This is one reason physicists love helium. It is simple enough to study deeply, yet rich enough to keep surprising people. It does not hide behind chemical complexity. There are no long molecular chains, no tangled reactions, no elaborate structure in the ordinary chemical sense. And yet, when cooled, it becomes one of the most subtle and revealing substances known. It shows that complexity does not always come from complicated ingredients. Sometimes complexity comes from simple ingredients placed under extreme conditions and allowed to follow quantum rules. In a story about sleep and science, one might wonder whether this wall-climbing liquid is calming or slightly alarming. Perhaps both. There is something unsettling about a liquid that refuses to stay in its cup. But there is also something soothing about its persistence. It does not burst out. It does not fight. It simply flows where flow is allowed. It reminds us that nature often chooses the path not of drama, but of least resistance. In the superfluid case, that phrase becomes almost literal. With ordinary resistance removed, the smallest path can matter. The thin film can become the road, the wall can become the riverbank, the rim can become a bend in the route rather than a barrier. If we were able to shrink down and watch the film from the scale of atoms, the scene would not look like a tiny version of water crawling up a wall. It would be governed by quantum behavior, by collective motion, by the shared state of the superfluid component. The atoms would not be little droplets marching in a line. The film would be a coherent layer with properties that belong to the whole. That is difficult to picture because our imagination prefers solid miniatures of everyday things. But the lesson is clear enough. The superfluid film is not a classical trick. It is the macroscopic surface expression of a quantum fluid. This is why the cup escape remains such a beloved image. It gives us a handle on something otherwise abstract. We may not easily picture a many-atom quantum state, but we can picture a liquid leaving a cup. From there, the mind can work backward. For the liquid to do that, the film must flow. For the film to flow that way, viscosity must be absent in the superfluid component. For viscosity to be absent, the atoms must be in a collective quantum state. For that state to exist, the helium must be cooled to the deep cold, where thermal motion no longer disrupts the coordination. The simple image becomes a trail leading all the way down to quantum mechanics. And now the polite rebellions start to look less like separate curiosities and more like symptoms of one underlying truth. Climbing walls, escaping cups, passing through tiny pores, maintaining persistent currents, carrying heat unusually well. All of these are different ways the superfluid state makes itself known. The liquid is not collecting tricks. It is expressing a new kind of order. Each odd behavior is a window into the same hidden structure. The wall is one window, the super leak is another, the long-lasting flow is another. Look through any of them, and you glimpse the fact that the helium is no longer an ordinary liquid. There is more to uncover inside that hidden structure. To understand why the whole liquid can behave with such coordination, we need to move beyond the image of a creeping film and into the deeper quantum picture, not with equations, and not with a rush into technical language, but with the basic idea that particles at low temperatures can stop acting like separate dancers and begin moving as part of one shared performance. The wall climbing is the visible sign. The escaping film is the quiet demonstration. Beneath it is the collective quantum dance of helium atoms, a dance so orderly and so strange that it turns a simple liquid into one of the most remarkable forms of matter ever found. Beneath the climbing film and the escaping cup, beneath the surface tricks that make superfluid helium seem almost mischievous, there is a quieter explanation. It is not the kind of explanation that feels natural at first, because it does not begin with tiny balls rolling around or little droplets pushing past one another. It begins with the fact that atoms are not quite the miniature solid objects our imagination wants them to be. They can behave like particles, yes, but they also have wave-like character, and when helium is cooled deeply enough, that wave-like character stops being a private detail of individual atoms and becomes the behavior of the whole liquid. That is the quantum dance inside superfluidity. Not a dance in the sense of steps across a floor, and not a dance with rhythm in any musical way, but a coordinated motion of matter where many atoms share one underlying state. At ordinary temperatures, this is nearly impossible to notice. The atoms in a gas or liquid are too busy. They rush, collide, scatter, and exchange energy in a jumble of motion. Each atom has its own little story, its own direction, its own tiny collisions, and the whole fluid behaves like a crowd where everyone is moving at once. We can still describe that crowd statistically, and the description works beautifully for ordinary fluids, but nothing about it suggests a single shared motion. It is too warm, too noisy, too restless. Cooling changes that. As the temperature falls, the random thermal motion fades. The atoms slow in the ordinary sense, and their wave-like nature spreads in importance. This is one of those phrases that can sound vague if we rush past it, So let us stay with it for a moment. In quantum mechanics, an atom is not only a point-like thing at one exact location with one exact motion, it is described by a wave-like state, a pattern of possibilities that tells us where it may be and how it may behave. At everyday scales, those wave-like patterns are usually too tiny or too disrupted to matter visibly. But helium atoms are light, and at low temperatures their quantum waves become large enough, relative to the distances between atoms, that the waves overlap. The atoms can no longer be thought of as completely independent little beads in a jar. Their identities begin to blur into something collective. This is where helium-4 becomes especially important. The atoms of helium-4 belong to a class of particles that are allowed to share the same quantum state in large numbers. That may sound like a technical detail, but it is the doorway. Some particles are antisocial in a very strict quantum sense. They refuse to occupy the exact same state. Others are more sociable. Helium-4 atoms are of the sociable kind. When the liquid is cooled enough, many of them can settle into a common state, not because they decide to cooperate, but because the laws of quantum mechanics permit and favour that collective arrangement. The result is a liquid where the behaviour of the whole becomes more important than the separate motion of each atom. A useful comparison is a crowd at a train station, but only as a first step. At rush hour, people move independently. Some hurry toward platforms, some stand in queues, some check phones, some suddenly stop in doorways for reasons known only to them and perhaps the pigeons. The crowd has patterns, but it is not moving as one. Now imagine that the random motion quiets, and a large portion of the crowd begins to move together in a coordinated way, not by instruction, but by shared condition. That is closer to the spirit of superfluidity. The atoms are no longer behaving like separate commuters in a busy station. A large part of the liquid enters a collective state where the motion belongs to the whole. Of course, the comparison fails if taken too literally. Atoms are not little people. They do not choose, hesitate, or wonder whether they have left the oven on. But the comparison helps with the main idea. Superfluidity is a collective phenomenon. It is not one helium atom being unusually slippery. It is not a few atoms sneaking through cracks while the rest behave normally. It is the liquid entering a state in which the quantum behaviour of many atoms locks together into one shared pattern. The strange properties come from the group. This is one of the great themes in physics. The behaviour of a group can be something entirely new, not just a larger version of the behaviour of its parts. A single water molecule is not wet. Wetness appears when many molecules gather and interact. A single iron atom is not a refrigerator magnet in your hand. Magnetism appears in materials when many microscopic magnetic tendencies align. A single bird is not a flock. A flock is a collective motion, a living pattern made from many individuals. Superfluid helium belongs to this family of emergent behaviour, but with a quantum twist. The whole liquid gains properties that individual atoms do not have by themselves. At low temperatures, the shared quantum state gives the superfluid a kind of coherence. Coherence means the parts are linked by a common pattern. In ordinary language, it is the difference between a noisy room full of people speaking over one another and a choir holding the same note. A choir is not just a louder person, it is a group acting together. In superfluid helium, the coherence is not sound but matter. The atoms are connected through a shared quantum description, and that shared description determines how the liquid can move. This coherence helps explain why the superfluid component flows without ordinary viscosity. In an ordinary liquid, one part of the fluid can rub against another. Layers move at different speeds and collisions transfer energy from smooth flow into random motion. That is viscosity at work. But in the superfluid component, the atoms are not behaving as a disordered collection of independent particles. The motion is part of a coherent quantum state. To slow that flow, the fluid would need to create disturbances that are allowed by the rules of that state. At low enough speeds, those disturbances cannot easily appear. The flow has no simple way to decay into ordinary heat. It is not merely that the atoms are moving smoothly, it is that the quantum state restricts how motion can be lost. This restriction is one of the deep reasons the fluid can seem so impossibly smooth. Ordinary friction is messy. It takes organised motion and scatters it into countless tiny movements. Superfluidity prevents that scattering in specific conditions. The flow cannot just bleed away in any small amount it likes. Quantum mechanics gives the system a kind of selectiveness. Certain disturbances are possible, others are not, and below a critical level of motion, the superfluid component simply has no available easy path to lose energy. It keeps going because the usual exits are closed. That does not make the superfluid fragile in the ordinary sense, but it does make it precise. If the flow becomes too fast, or if the liquid is disturbed strongly enough, it can create excitations. These are disturbances in the quantum fluid, little packets or patterns of energy that can carry motion away. Some are related to sound like waves. Others are more unusual and specific to the quantum liquid. When such excitations appear, the superfluid can experience drag or dissipation. So the state is not a miracle blanket thrown over all motion. It has conditions. At gentle enough flow, the motion can remain almost perfectly free. Push too hard, and the liquid finds ways to respond. That balance between freedom and rule is part of what makes superfluidity so beautiful. It is not chaotic strangeness, it is disciplined strangeness. The liquid does not do anything whatsoever. It does certain impossible-looking things for exact physical reasons. It climbs walls because a superfluid film can move along surfaces. It passes through narrow paths because the superfluid component lacks ordinary viscosity. It carries heat in unusual ways because the normal and superfluid components can move relative to one another. It forms quantized vortices because its rotation is governed by the shared quantum state. Each strange behaviour is connected to a deeper order. The two-fluid picture helps us navigate this order without getting lost. Below the transition temperature, liquid helium behaves as though it contains a normal component and a superfluid component. Again, these are not two separate liquids layered like salad dressing. They are two kinds of motion within the same helium. The normal component carries heat and entropy, and it has viscosity. The superfluid component carries no entropy and flows without ordinary viscosity. As the temperature drops, the superfluid component grows. At the coldest reachable conditions, nearly all the liquid behaves as superfluid. This picture is not just a convenient metaphor. It explains real measurements and real behaviour, while giving the mind something gentler to hold than a full quantum theory. The normal component can be thought of as the part of the liquid associated with thermal excitations, the remaining restless disturbances that exist because the temperature is not exactly at the lowest possible limit. The superfluid component is the coherent ground state, the calm collective behaviour underneath. As the liquid gets colder, there are fewer thermal excitations, and the normal component shrinks. This is why the superfluid properties become stronger deeper in the cold. The random motion is not merely reduced, the coherent part becomes dominant. Here is where the dance image returns, but in a more careful way. Imagine a floor where some dancers are moving in scattered patterns, while others are part of a single coordinated formation. At higher temperatures, the scattered motion dominates. The formation exists only weakly or not at all. Lower the temperature, and more of the dancers join the coordinated motion. The floor becomes less random, more unified. Eventually, the coordinated formation controls the character of the whole scene. The normal component has not become a different substance. It is the disorder left in the system. The superfluid component is the ordered quantum motion that emerges as the disorder fades. The word order can be a little misleading, because superfluid helium is still a liquid. It is not ordered like a crystal, with atoms fixed in a repeating pattern. It has no rigid lattice. It flows. It has no ordinary solid structure. Its order is not spatial in the simple crystal sense. It is quantum order. It is order in the shared state of motion and phase, in the coherence of the atoms. That makes it harder to picture, but also more fascinating. The liquid remains liquid, yet gains a hidden internal unity. This is why helium is such a special case. Many substances, when cooled, become solids before such a superfluid state can appear. Their atoms settle into fixed positions. The chance for large-scale quantum liquid behavior is lost because the material has frozen into a crystal. Helium avoids this because its atoms are light and weakly attracted. Their quantum motion keeps them from freezing under ordinary pressure. It remains liquid, and because it remains liquid at extremely low temperatures, it can enter the superfluid state. Helium gives quantum mechanics room to move. There is a quiet irony in that. We often think of quantum effects as delicate and hidden, easily destroyed by the messy real world, and that is often true. But in liquid helium, the very simplicity and stubbornness of the element allow quantum behavior to become robust on a visible scale. The liquid does not need complicated chemistry. It does not need elaborate molecular machinery. It only needs helium atoms, extreme cold, and the permission granted by quantum statistics. From that, the extraordinary emerges. The shared state also changes how the liquid responds to being rotated. This is one of the most striking differences between a superfluid and an ordinary liquid. If you rotate a bucket of water, the water eventually begins to rotate with the bucket. Its surface curves, and the whole fluid moves more or less like a spinning body, because viscosity transfers motion from the container wall inward. The walls drag the adjacent water, that water drags the next layer, and after a while the whole mass is involved. Superfluid helium does not respond in that simple way. Without ordinary viscosity, the superfluid component cannot simply be dragged into smooth rotation by the walls. Instead, when rotation is strong enough, the superfluid forms vortices. These are tiny whirlpools, but not ordinary whirlpools with any possible strength. Their circulation comes in fixed quantum amounts. The fluid organizes rotation into discrete threads. Each vortex is like a narrow line around which the superfluid circulates. In a rotating container, many vortices can arrange themselves in a regular pattern, allowing the superfluid as a whole to mimic rotation, while still obeying quantum rules. It is as if the liquid refuses smooth, ordinary spinning, but agrees to rotate through a collection of approved little whirlpools. Very formal, very strange, and quite beautiful. Those vortices are not just decorative, they reveal the structure of the quantum state. Because the superfluid is coherent, its motion must obey strict rules. The circulation around a vortex is tied to the wave-like nature of the fluid. The state must fit together consistently around a closed path. If that sounds abstract, think of it like walking around a circular track and needing to end in step with where you began. Only certain patterns fit neatly. In superfluid helium, this consistency requirement means rotation comes in specific units. The liquid cannot choose any circulation it likes. It chooses from the allowed set. This is one of the clearest signs that the superfluid is a macroscopic quantum object. Macroscopic simply means large enough to be observed on our scale. A single atom obeys quantum rules, but that is expected. A visible liquid forming vortices with quantized circulation is another matter. That is quantum mechanics leaving fingerprints across an entire fluid. The dance of atoms is not hidden in the microscopic details. It shapes the motion of the whole. The same coherence influences sound and heat. In ordinary fluids, sound travels as pressure waves. Regions of compression and rarefaction move through the material. Superfluid helium can support ordinary sound, but it also supports a second kind of wave, a wave of temperature and entropy. In this motion, the normal and superfluid components move in relation to each other. Heat does not merely diffuse slowly outward, as it often does in ordinary materials. It can travel like a wave through the liquid. This is another sign that the two components are not a decorative idea, but a real description of how the liquid behaves. It is difficult not to admire the elegance of that. A single liquid, clear and simple looking, contains two interwoven modes of motion. One carries entropy, the other does not. One has viscosity, the other does not. Together, they allow heat to move in ways that ordinary liquids cannot match. If you only looked at the surface, you might miss everything. The liquid seems calm. Inside, it is performing one of the most refined acts in condensed matter physics. Condensed matter physics is the study of how matter behaves when many particles interact. It may not sound as dramatic as black holes or exploding stars, but it contains some of the deepest surprises in science. It asks what happens when particles gather in huge numbers and produce new collective behavior. Crystals, magnets, superconductors, semiconductors, superfluids all belong to this broad world. The phone in a pocket, the magnet on a refrigerator, the sensors in a hospital machine, and the strange helium in a cryogenic vessel all depend on the fact that many particles together can create properties no single particle has alone. Superfluidity is one of the finest examples because it shows collective quantum behavior so clearly. The atoms are not acting as isolated individuals. They are participating in a state that belongs to the whole liquid. And this state has consequences that can be observed directly. It is not a philosophical claim hidden in interpretation. It is a physical reality measured through flow, heat, rotation, and surface films. Quantum mechanics, often treated as something remote and abstract, becomes the reason a liquid climbs over a wall. This brings us back to the film. The film is not a side effect unrelated to the quantum dance. It is one of its visible expressions. The superfluid order can extend through the thin layer along the surface. Because the layer can support superfluid flow, the liquid can move over the rim. The surface becomes a path for the coherent state. The film is thin, but the quantum behavior does not require a large depth to matter. Even a delicate layer can carry the strange motion, so long as the conditions support it. A person watching this might feel that the liquid is too continuous, too unified, almost as though it has become one object rather than a collection of atoms. That intuition is not entirely wrong, provided we treat it gently. The atoms do not fuse into a single particle. They remain helium atoms, but their collective quantum state gives the liquid a unity that ordinary fluids lack. The whole has a shared phase, a shared coherence, a shared set of rules for motion. It is many atoms, yet one fluid in a deeper sense than water is one fluid. Water is unified by contact and interaction. Superfluid helium is unified by a quantum state. There is a common phrase in physics that says nature does not care about our intuition. It is true, though perhaps a little stern for bedtime. A softer version is that intuition is local. It comes from the conditions we know. We learn from warm matter, moderate speeds, ordinary gravity, and objects large enough to touch. Quantum fluids live outside that training ground. They are not irrational. They are simply obeying rules we do not meet at breakfast. Once those rules are understood, the behavior becomes less like nonsense and more like a different kind of sense. This different kind of sense also explains why superfluidity cannot be reduced to one simple cause like cold alone. Cold is necessary, but cold is not the whole story. A cold rock is not superfluid. A cold spoon does not flow up a wall, thankfully. The particles must have the right quantum properties. The substance must remain liquid. The thermal motion must fall low enough for coherence to appear. The interactions must allow the collective state to form. Superfluidity is a precise meeting of conditions. Extreme cold opens the door, but helium's quantum nature walks through it. There are other superfluids beyond helium-4. Helium-3 can become superfluid at even lower temperatures, but through a more complex mechanism involving paired atoms. Ultra-cold gases made in laboratories can also enter related coherent states, allowing physicists to study quantum fluids in carefully controlled ways. These systems show that superfluidity is not a one-off curiosity. It is a broader phenomenon, a recurring possibility in matter when particles organize collectively at low energy. Helium remains the classic case because its behavior is so vivid, but it belongs to a larger family of quantum fluids. That broader family matters because it connects superfluidity to other parts of the universe. Inside neutron stars, for example, matter may exist in superfluid states under pressures and densities far beyond anything on Earth. These stars are the collapsed remnants of massive stars, so dense that a spoonful of their material would be unimaginably heavy. Their interiors are not places we can visit or sample, which is probably for the best, but physics suggests that neutrons inside them may form superfluid components. The same basic idea of collective quantum motion may help explain how these stars rotate, glitch, cool, and evolve. A flask of cold helium in a laboratory can therefore teach us something about the hearts of dead stars. That is the sort of connection physics makes when it is in a generous mood. Yet even without neutron stars, the quantum dance of superfluidity is enough. It tells us that matter can become more than matter in the everyday sense. It can become organized possibility. It can move without ordinary loss, rotate through quantized vortices, carry heat as waves, and climb surfaces through films so thin they barely seem real. All of that comes from atoms obeying quantum rules together. Not one atom, not a handful, a liquid full of them. There is a calmness in this picture that suits the deep cold where it occurs. The noisy world fades, thermal motion quiets, randomness retreats, a shared state emerges. The liquid becomes smooth in a way that is not merely visual, but physical. It flows with a kind of collective discipline. It does not become simple exactly. The theory is rich, and the experiments are subtle, but the central idea is clear enough to rest with. When helium is cooled far enough, its atoms stop behaving only as separate restless particles and begin acting as a coherent quantum whole. From that whole, superfluidity appears, and once that whole exists, rotation cannot be ordinary, because the fluid's motion must fit the quantum state. Disturbance cannot be ordinary, because energy can only be lost through allowed excitations. Flow cannot be ordinary, because viscosity is absent from the superfluid component. Boundaries cannot be ordinary, because a thin film can carry the coherent liquid along a surface and over the edge. The familiar world remains in the background, but it is no longer in charge. So the climbing wall was never just a trick, it was the surface sign of something deeper. The escaping cup was not a curiosity separated from the theory. It was the visible edge of a quantum state large enough to fill a vessel. Inside the liquid, the atoms are not dancing in the lively, messy sense of warm matter. They are participating in a shared, ordered, low-temperature motion where the whole fluid gains new rules. To follow those rules further, we have to look at what happens when this strange liquid is forced to turn, swirl, and respond to motion. Because in the superfluid world, even a whirlpool is not allowed to be casual. It must obey the hidden structure of the quantum dance, forming vortices that reveal the shape of motion itself. Once the superfluid is asked to turn, the strangeness becomes easier to see and harder to ignore. Flowing in a straight path is already unusual enough when ordinary friction has gone missing, but rotation is where the liquid reveals just how different it is from water, oil, or any ordinary fluid swirling in a cup. If you spin a bowl of water, the water gradually joins the motion. The layer touching the bowl is dragged along first, then the next layer, and then the next, until the whole body of water begins to rotate. The surface curves slightly, the center dips, the outside rises. It is a familiar scene, even if most of us do not stare deeply into rotating buckets, unless we are either physicists or very bored while washing dishes. This ordinary rotation depends on viscosity. The walls drag the nearby fluid drags the fluid beside it, and the motion spreads inward. Viscosity acts like a messenger carrying the rotation through the liquid. It is not a perfect messenger, and sometimes it creates turbulence, swirls, and eddies along the way, but it gets the message across. The container turns, and after a while the fluid turns with it. This is such a normal process that it can feel obvious. But in a superfluid, the messenger is missing. The superfluid component has no ordinary viscosity, so the container cannot simply grab the fluid by friction and drag it into smooth rotation. The liquid refuses the usual invitation. At first, this sounds as if a superfluid should never rotate at all. If the walls cannot drag it, perhaps it should sit still while the container spins around it, like a very calm passenger on a wildly rotating fairground ride, which is not a recommended bedtime image. But nature rarely chooses the simplest version of weird. Superfluid helium does not rotate like an ordinary liquid, but it can still respond to rotation. It does so by forming vortices. These are tiny whirlpools, narrow lines around which the superfluid circulates. They are not messy swirls of the ordinary kind. They are organised, precise, and governed by quantum rules. A vortex in an ordinary fluid can come in nearly any strength. Stir water gently, and you make a weak swirl. Stir it harder, and you make a stronger one. A river eddy can be broad and lazy or tight and fast. A draining bathtub can form a whirlpool that depends on the shape of the tub, the movement of the water, and the small disturbances present at the start. Ordinary vortices are flexible, variable, and somewhat untidy. They belong to a world where motion can be divided and shared in almost any amount. Superfluid vortices are different. Their circulation comes in fixed units. The liquid cannot choose just any amount of swirl. It must use the allowed amounts, as though the universe has turned rotation into a staircase rather than a slope. This is one of the clearest signs that superfluid helium is not an ordinary liquid with unusually good manners. It is a quantum fluid. The motion of the whole liquid is constrained by the wave-like state shared by the atoms. The superfluid has a kind of internal consistency it must maintain. If the fluid circulates around a vortex, the quantum state has to fit neatly around the loop. It cannot come back mismatched. That requirement forces the circulation into discrete values. The vortex is not merely a spinning motion. It is a topological feature of the quantum state, though we can say that more gently. It is a place where the liquid's shared motion wraps around a central line in one of the permitted ways. At the very centre of a vortex, something especially interesting happens. The superfluid state cannot remain fully intact at the core. The circulating motion would become too extreme if it continued all the way to the exact centre. So the vortex has a tiny core where the superfluid order is suppressed. Around that core, the liquid circulates. In a sense, the vortex is a whirlpool wrapped around a thread of not quite superfluid. That is why the phrase "the shape of nothingness" feels appropriate, as long as we keep our feet on the ground. The vortex is not a hole in reality. It is not empty space in the dramatic science fiction sense, but it is a narrow line where the normal smooth superfluid order breaks down, and around that line the quantum fluid organises its rotation. This is wonderfully strange. In ordinary thinking, a whirlpool is made of water turning. The centre may be a dip or an air column, but the idea is familiar. In superfluid helium, the vortex is partly defined by what cannot exist at its centre. The shared quantum state has to step aside. The core becomes the line around which the permitted motion is arranged. The vortex is a structure made from circulation around a tiny absence of superfluid order. It is motion given shape by a constraint. A little nothing in the middle, surrounded by something moving in a very exact way. When a container of superfluid helium is rotated slowly, the liquid may resist ordinary rotation. Increase the rotation beyond a certain point, and vortices begin to appear. Add more rotation, and more vortices form. Rather than spinning smoothly like water, the superfluid builds rotation out of many tiny quantized whirlpools. In a rotating vessel, these vortices can arrange themselves in orderly patterns, often forming a regular array. If one could see them clearly, the effect would look almost like a lattice of slender threads running through the liquid, each carrying its fixed unit of circulation. The whole superfluid then mimics rotation through the combined effect of these vortices, while still obeying the quantum rules that forbid ordinary smooth spinning. That is a remarkable compromise. The container says, rotate. The superfluid says, not in the usual way. The universe says, use vortices. And so rotation is broken into many little approved channels. It is like a city that refuses to allow random shortcuts, but provides a precise grid of the roads. Motion is permitted, but only in the allowed forms. This is not stubbornness, of course. The liquid has no opinions about traffic planning. It is quantum mechanics expressed through fluid motion. Vortices are not just a curiosity, they matter because they are one of the main ways superfluids can lose energy and interact with their surroundings. Remember, the superfluid component can flow without ordinary viscosity, but it is not immune to all forms of disturbance. If a superfluid moves too fast past an object, or if conditions become unstable, vortices can form. Once vortices appear, they can carry energy, they can tangle, they can reconnect, they can create drag in ways that ordinary viscosity does not. In other words, the superfluid can still become complicated, but the complications arrive through quantum-approved structures rather than ordinary friction. This point is important because superfluidity can sound too perfect if described too quickly. A fluid without viscosity might seem like a fluid without consequences, a liquid that simply glides forever no matter what happens. But real superfluids live in real containers, with surfaces, temperatures, disturbances, and limits. Their motion can be stable and persistent, but only under the right conditions. Vortices are one of the ways the superfluid reveals those limits. They are the bridges between ideal frictionless flow and the messy world of actual experiments. They show how a fluid with no ordinary viscosity can still respond, adjust, and sometimes dissipate energy. Imagine moving a small object through superfluid helium. If it moves gently enough, the superfluid may flow around it without producing drag in the ordinary way. The motion remains smooth, and the object does not lose energy through normal viscous resistance. But if the object moves faster than a certain threshold, the liquid can no longer accommodate the disturbance so quietly. It may create excitations, including vortices, and those excitations carry energy away. The object then experiences resistance, not ordinary viscosity, but a different kind of drag produced by the creation of disturbances in the quantum fluid. The superfluid has not broken its promise. The promise was simply more precise than our first impression. This is a recurring theme in physics. The most interesting statements are often not absolute in the everyday sense. They are conditional. A superfluid flows without ordinary viscosity below certain speeds and under certain circumstances. A superconductor carries current without ordinary resistance below certain limits. A material may be transparent to some wavelengths but not others. A star may be stable until its mass crosses a threshold. Nature gives us clean laws, but the boundaries matter. Superfluid vortices live at the boundaries. They appear when the liquid needs a permitted way to handle rotation or disturbance. The study of vortices also makes superfluid helium feel surprisingly visual. Quantum mechanics is often described as abstract, hidden in equations and probability. But vortices are structures. They can be detected. They can be arranged. In some modern experiments with other superfluid systems, especially ultra-cold gases, vortex arrays can be imaged directly. They appear as patterns, tiny holes or dips in the density where the vortices pass through. The quantum state, normally invisible, draws a map of itself. It is as if the liquid has written its own motion into a pattern that instruments can read. In helium, seeing vortices directly is more challenging, but scientists have developed clever methods. Tiny particles can become trapped on vortex lines, making the vortices easier to trace. Waves and measurements can reveal their presence. The behavior of rotating helium can be studied through its effects. This is one of the pleasures of experimental physics. If nature hides the thing you want to see, you find a way to make its shadow visible. A vortex line may be too small and delicate to observe casually, but its influence is not silent. The idea of vortex lines leads to another strange image. A superfluid vortex is not just a little spinning patch. It can stretch through the liquid as a filament. It can bend. It can move. It can interact with other vortices. In turbulent conditions, many vortices can form a tangled mess, a quantum version of turbulence. Ordinary turbulence, like the chaotic motion behind a fast-moving boat or in smoke rising from a candle, is already one of the hardest problems in classical physics. Quantum turbulence adds another layer of strangeness, because the vortices are quantized. The tangle is messy in shape, but its building blocks are precise. Chaos made from identical little threads. That phrase should not be made too grand, but it is a useful picture. In ordinary turbulence, swirls can break into smaller swirls in a continuous cascade of motion. In a superfluid, circulation is divided into quantized vortex lines. The turbulence is built from these lines interacting, tangling, and sometimes reconnecting. It is not simpler than ordinary turbulence, but it is different in a way that gives physicists a new handle. Superfluid helium becomes a laboratory for studying how disorder can arise, even when the fundamental units of rotation are strictly controlled. There is also a deep connection between vortices and the earlier idea of persistent flow. In a closed loop, superfluid current can persist because ordinary friction cannot drain it away. But the flow can change if a vortex crosses the flow path. A vortex can allow the superfluid to shift from one allowed circulation state to another. This is one way the liquid can lose or adjust its flow. Again, the superfluid cannot simply slow by any tiny amount it pleases. It changes through permitted events. Vortices provide those events. They are the release valves of the quantum flow. The release valve makes them sound far more mechanical than they are. If the motion of the superfluid is like a perfectly smooth road with no ordinary friction, vortices are the places where the road can change route. They are not defects in the careless sense. They are necessary structures. Without them, the superfluid could not rotate properly. Without them, it would have fewer ways to respond to strong disturbances. They are both signs of order and agents of change. That dual role makes them especially interesting. A vortex is a flaw in the smooth superfluid order, but a flaw required by the larger order of the system. A little imperfection that makes the whole possible. This may sound familiar from other parts of physics and even from everyday life. Crystals can contain defects, and those defects often determine how the material bends, breaks, or conducts electricity. A perfectly uniform system may be simple, but real behavior often depends on the imperfections. In superfluid helium, vortex lines are not impurities or dirt. They are topological defects, meaning they are stable features tied to the structure of the state itself. That phrase is technical, but the idea is not impossible. The vortex exists because the fluid's shared quantum motion wraps around it in a way that cannot be smoothed out casually. To remove it, the system must undergo a real change, not just gently rearrange itself. The word topological can be approached through a simple image. Imagine a loop of string tied in a knot. You can pull and twist the string, but unless you cut it or pass an end through, the knot remains. The knot is not defined by the exact shape of the string at any moment. It is defined by how the string is connected. A vortex has a similar stubbornness. Its existence is tied to how the quantum state winds around the core. The details can shift, the line can bend, but the basic winding cannot simply disappear unless the system allows a process that removes it. This gives vortices a kind of durability. In a rotating superfluid, a whole array of these durable lines can form. The number of vortices depends on how fast the container rotates. More rotation calls for more vortices. The spacing between them reflects the overall motion. The superfluid is translating the smooth rotation of the container into a pattern of discrete vortex lines. This is one of those places where the microscopic and macroscopic meet. A laboratory-scale rotation becomes a countable pattern of quantum whirlpools. The atoms are small, but the rule they follow shapes the entire fluid. The shape of nothingness also appears in the vortex core because that core is where density or superfluid order is reduced. It is not a large empty tunnel, but it is a line of altered state. Around it, the liquid circulates. The core gives the circulation somewhere to wrap around. If there were no core, the mathematical description of the flow would become impossible at the exact center. Nature avoids that by changing the local state. The vortex is therefore both motion and structure. It is not just flow around a point, it is a physical object of a peculiar kind, a thread in the liquid defined by the absence of the very order that surrounds it. This can feel almost too subtle, but the consequences are real. Vortices can influence how the superfluid transfers angular momentum, which is the rotational form of motion. They can pin to surfaces or impurities. They can move through the liquid. In systems like neutron stars where superfluid matter may exist under extreme density, vortex behavior may help explain sudden changes in rotation known as glitches. A neutron star can spin with incredible regularity, then suddenly shift its rate slightly. One explanation involves the motion and unpinning of vortices in the superfluid interior. That means the same basic physics glimpsed in cold helium may help us understand the behavior of collapsed stars far across the galaxy. It is worth sitting with that connection for a moment. In a laboratory on Earth, helium is cooled until it becomes superfluid. In the dense interior of a neutron star, matter may become superfluid for entirely different reasons, under conditions of pressure and density beyond ordinary imagination. Yet vortices appear in both stories because rotating superfluids need a way to handle angular momentum. The details differ enormously, but the underlying principle echoes. Quantum fluids do not rotate like normal fluids. They build rotation from vortices. A tiny cryogenic vessel and a dead star may share a hidden grammar of motion. That is one of the reasons physicists care so much about these strange liquids. Superfluidity is not just a party trick of helium. It is a window into how matter behaves when quantum rules organize motion on large scales. Vortices are among the clearest features of that window. They show that motion itself can be quantized, not just energy in an atom, not just light emitted in discrete packets, but the swirling of a visible fluid. The whirlpool in the superfluid is an announcement that quantum mechanics has climbed up from the microscopic realm and left a mark on something we can, least in principle, watch. There is also a practical emotional contrast here. A whirlpool usually suggests chaos, danger, water pulling downward, motion becoming uncontrollable. In a superfluid, vortices are not necessarily chaotic. A single vortex is orderly. An array of vortices is orderly. Even a tangle of vortices has precise building blocks. The superfluid turns rotation into a kind of structured complexity. It is not the wild swirl of stirred cream. It is the disciplined response of a coherent quantum liquid. If ordinary turbulence is a crowd shouting over itself, a vortex array is more like a carefully seated orchestra, although the instruments are invisible and extremely cold. The role of frictionless motion becomes clearer through this. Frictionless does not mean featureless. It does not mean motion without structure. It means the absence of ordinary viscous resistance. In fact, because ordinary viscosity is absent, the remaining forms of motion become more sharply defined. Vortices stand out. Persistent currents stand out. Temperature waves stand out. The lack of ordinary friction does not make the fluid boring. It reveals a different set of rules with greater clarity. That is why superfluid helium is such a useful teacher. It takes away one of the most familiar sources of messiness, ordinary viscosity, and shows us what remains. What remains is not nothing. It is a world of quantum constraints, coherent flow, allowed excitations, and quantized vortices. The superfluid is smooth, but not empty. It is calm, but not simple. It can move without ordinary loss, but it still has a rich inner life. Its motion is not a blank glide. It is a carefully governed form of collective behavior. If one wanted to describe the shape of nothingness without becoming too poetic, one could say this. A vortex is a narrow region where the superfluid order is reduced, surrounded by circulation that can exist only in fixed quantum amounts. That is the plain version, and it is already strange. The liquid organizes motion around a line where its special order cannot fully exist. The absence at the core helps define the presence around it. It is a physical structure made from both matter and constraint. This idea of constraint is central. Superfluids are not free because they have no rules. They are free from ordinary friction because they obey deeper rules. Their motion persists because not every energy loss is allowed. Their rotation is quantized because not every swirl is allowed. Their vortices are stable because not every deformation can erase them. Freedom, in this case, comes from restriction. That may sound counterintuitive, but physics is full of such trade-offs. A train can move smoothly because tracks restrict where it goes. A musical note is clear because a string vibrates in allowed patterns. A superfluid flows so perfectly because its quantum state restricts the ways it can be disturbed. The more we follow those restrictions, the less superfluidity feels like a violation of common sense, and the more it feels like common sense was simply trained in the wrong place. We learned about liquids from warm, noisy matter. We learned about rotation from water in bowls and air in storms. We learned about friction from surfaces that heat and objects that slow. Superfluid helium lives in a quieter region of physical law. It is not more mysterious because the laws are weaker. It is more mysterious because the laws are more exacting. The story of vortices also prepares us to think beyond helium itself. Superfluids reveal that the universe permits collective states where motion becomes organized in ways that feel almost unreal. They show that quantum mechanics is not limited to the tiny and inaccessible. They connect laboratories to stars, liquids to fields, cold atoms to cosmic rotation. A small vortex line in helium and a possible vortex inside a neutron star are separated by enormous differences in scale and environment, but both arise from the same need for a quantum fluid to handle rotation. So when we return to the image of a liquid climbing a wall, it no longer stands alone. It belongs to a family of behaviors. The film flow shows how surfaces become paths. Persistent currents show how motion can remain without ordinary drag. Vortices show how rotation becomes quantized. Together they reveal a liquid whose behavior is shaped not by the rough habits of everyday matter, but by the coherence of a shared quantum state. The superfluid is not just smooth, it is organized, not just cold, it is deeply ordered in motion, not just strange, it is strange in a way that teaches, and that leads naturally to the wider meaning of all this. Superfluids are not only laboratory curiosities, and they are not only impressive examples for physics lectures, they are clues. They help us understand how many particles can act together as one, how resistance can vanish, how rotation can be broken into quantum threads, and how matter under extreme conditions may behave in places we cannot touch. They invite us to reconsider what a liquid can be, what motion can be, and how much of the universe remains hidden simply because we usually meet matter at comfortable temperatures. From the small cold vessel of helium, the path begins to open outward, towards superconductors, ultra-cold atoms, neutron stars, and the deeper question of what these strange fluids reveal about reality itself. Superfluids reveal something very simple at first, and then something much larger. The simple part is that liquids are not as ordinary as they seem. A liquid can be more than a substance that pours from one container to another. It can be a stage where quantum mechanics becomes visible. It can carry motion without ordinary friction. It can climb surfaces as a thin film. It can rotate through tiny vortex lines rather than by smooth swirling. It can hold a current for so long that the usual meaning of slowing down begins to feel incomplete. These are not small curiosities added to the edge of physics. They are signs that matter can organize itself in ways our everyday experience would never predict. Most of the time, the quantum world feels far away. We hear about atoms, electrons, wave functions, probabilities, and particles behaving in ways that seem to belong to instruments and equations rather than to rooms, cups, and visible liquids. Quantum mechanics is often introduced as the science of the very small, and that is understandable. Its strangeness first becomes unavoidable when we look at atoms and subatomic particles. But superfluidity shows that quantum behavior does not have to stay microscopic. Under the right conditions, the rules that govern tiny things can rise into view at a scale we can measure directly. A whole liquid can become quantum in its motion. Not just one atom, not just a few particles, a visible amount of matter in a laboratory vessel. That is one of the first lessons superfluids teach. The boundary between the quantum world and the everyday world is not a hard wall. It is more like a change in conditions. At ordinary temperatures, random thermal motion tends to hide collective quantum effects. Everything is too busy, too noisy, too full of jostling particles for delicate coordination to dominate. But cool helium deeply enough, and the noise fades. The wave-like nature of the atoms begins to matter not just as a private property of each atom, but as a shared property of the liquid. The result is not a vague mystery. It is a physical state with measurable consequences. The liquid flows differently, carries heat differently, rotates differently, escapes containers differently. Quantum mechanics has stepped into the visible world. This matters because it corrects a common misunderstanding. Quantum mechanics is not merely a strange set of rules for tiny objects. It is part of the structure of all matter. It is always there, in a stone, in a glass of water, in your hand resting under a blanket, in the air moving through the room. We do not usually notice it directly because the large, warm world averages it out. The countless motions and interactions blur the details. Superfluids are special because they remove enough of that blur to let the deeper order show through. They are not separate from the universe we know. They are the universe under carefully chosen conditions, revealing a side of itself that is normally hidden by warmth. They also show that resistance is not as fundamental as it feels. In daily life, resistance is everywhere. A door hinge creaks, a bicycle slows, a spoon dragged through thick soup meets drag. Electricity in an ordinary wire loses energy as heat. Air pushes against a moving car. Water stirred in a bowl eventually rests. We grow up assuming that motion naturally runs down, that everything moving must eventually fade unless something keeps pushing. That assumption is sensible for the world we live in, but superfluidity tells us it is not the whole truth. Motion does not always have to decay in the ordinary way. Under the right quantum conditions, a flow can persist because the usual path for losing energy is not available. This does not mean nature offers a loophole for free energy. That is important. Superfluids do not create energy from nothing. They do not allow machines to run forever while doing work without cost. The laws of thermodynamics remain firmly in place, and they are not known for making exceptions just because something looks impressive in a cryogenic vessel. What superfluids reveal is more precise and more interesting. They show that the mechanisms of loss depend on the state of matter. In an ordinary liquid, organized motion can easily scatter into random molecular motion. In a superfluid, the collective quantum state restricts how that scattering can occur. Below certain speeds and under certain conditions, the flow cannot simply break down into heat. So it persists. That one idea reaches far beyond helium. It connects to superconductivity, where electrical current moves without ordinary resistance in certain materials. It connects to ultra-cold atomic gases, where scientists cool atoms until they enter coherent collective states and behave like quantum fluids. It connects to the deep interiors of neutron stars, where dense matter may form superfluid components under conditions that are almost impossible to imagine. It even connects to the broader idea of emergence, the way many small parts can produce a whole with properties no single part possesses alone. A single helium atom is not superfluid. A single electron is not a superconductor. A single molecule of water is not wet. These properties appear when many particles interact and organize together. Emergence is one of the great quiet themes of the universe. It is not the same as magic, though it often feels surprising. It means that when pieces come together in the right way, new behavior appears. The new behavior is real, even though it cannot be found inside one isolated piece. Wetness is real. Magnetism in a material is real. The stiffness of a crystal is real. The memory of a computer chip is real. Life itself depends on emergent organization, with molecules arranged into cells, cells arranged into tissues, and tissues arranged into thinking creatures who sometimes stay awake, listening to explanations of helium. Superfluidity belongs to this same broad family, but it is unusually clean. It shows emergence at its most quantum, where the group behavior comes from many particles sharing a coherent state. That is why superfluids are so valuable scientifically. They give physicists a relatively pure system for studying collective behavior. Helium is chemically simple. It does not form complicated molecules. It does not hide behind layers of chemical reactions. Its atoms are plain by the standards of matter, and because of that plainness, the quantum behavior becomes easier to isolate. This does not mean the theory is easy. It is not. But it does mean helium can act as a kind of clear window. Through that window, scientists can study how coherence appears, how vortices form, how frictionless flow persists, and how a many-particle system behaves when ordinary thermal disorder is reduced. The lessons from superfluids also help us think about the universe in extreme places. Earth is comfortable enough for our kind of life, but most of the universe is not arranged for comfort. There are regions of intense heat, deep cold, crushing pressure, strong gravity, and enormous magnetic fields. Matter in those places does not always resemble the matter in a kitchen or a laboratory at room temperature. Inside neutron stars, for example, the remnants of massive stars collapse matter to extraordinary densities. The atoms as we know them are gone. Protons, neutrons, and electrons are forced into states far beyond normal matter. Physics suggests that some of the particles inside these stars may form superfluid or superconducting phases. We cannot scoop out a sample and place it on a bench, which is probably fortunate for the bench. But by studying superfluids on Earth, scientists gain tools for thinking about how such exotic matter might move, rotate, and store energy. This becomes especially interesting because neutron stars spin. Some rotate many times each second with remarkable regularity. Yet some of them occasionally undergo sudden small changes in rotation, often called glitches. One possible explanation involves superfluid matter inside the star and the behavior of vortices. In a rotating superfluid, motion is carried by quantized vortex lines. If those vortices become pinned and then suddenly shift, they can transfer rotational motion to the outer part of the star. The details are complex, and neutron stars are far more extreme than any helium experiment, but the connection is powerful. A cold liquid on Earth teaches us how quantum fluids rotate, and that knowledge helps us interpret signals from dense stars far away. There is something deeply satisfying about that. A vessel of helium in a laboratory and a neutron star in space have almost nothing in common at first glance. One is small, carefully cooled, and studied by instruments. The other is a collapsed stellar core with gravity so intense that ordinary language begins to fail. Yet both may share the language of superfluid motion. Both can contain fluids where rotation is not smooth and continuous in the ordinary sense, but organized through vortices. Physics often works this way. It finds patterns that repeat across wildly different scales. The universe is not the same everywhere, but it often uses similar principles in different settings. Superfluids also reveal that emptiness and structure are not opposites in the simple way we might think. A vortex in a superfluid has a core where the superfluid order is reduced, and around that core the liquid circulates. The structure depends on something missing at the center. It is a reminder that absence can have physical meaning. In many areas of physics, what is not there matters as much as what is there. A hole in a semiconductor can behave like a particle. A boundary can determine the behavior of a material. A defect in an ordered state can shape how the whole system responds. Superfluid vortices are part of this wider lesson. The liquid is not only made of atoms, it is made of order, constraints, and the ways that order can fail locally while still shaping the whole. That may sound abstract, so it helps to bring it back to the cup. The superfluid climbs the wall because a thin film can support superfluid flow. That film is not impressive by size. It is not a roaring river. It is not a wave crashing across a beach. It may be too thin to see easily, yet it changes the practical reality of the container. The wall becomes a path, the rim becomes a bend, the outside becomes a continuation of the route. A tiny layer of matter governed by a shared quantum state changes what containment means. This is a very concrete example of a larger truth. Small structures and thin boundaries can control large outcomes. The same is true in much of modern physics and technology. Thin layers in electronic devices control currents and signals. Surfaces of materials determine chemical reactions. Interfaces between substances shape everything from batteries to biological membranes. Physics is not only about bulk matter, but about edges, films, defects, and boundaries. Superfluid helium makes that lesson memorable because its thin film can literally carry the liquid out of a container. It is difficult to forget a boundary after watching it become a road. Superfluids also help us see the importance of temperature as more than comfort or weather. Temperature is a measure of thermal energy, and changing it can reveal entirely new phases of matter. At familiar temperatures we meet solids, liquids, and gases. Those categories are useful, but they are not complete. Lower the temperature enough, and matter can enter superconducting, superfluid, and other coherent phases. Raise the temperature enough, and matter can become plasma. Under high pressure, it can form structures that do not exist at ordinary conditions. The universe contains more states of matter than the simple list we learn first. Superfluidity is one of the most vivid reminders that matter has hidden rooms, and temperature is one of the keys. This does not make ordinary matter less important. Water is still astonishing. Air is still subtle. Ice is still rich in structure. But superfluidity expands the map. It shows that the familiar world is not the full world. Our intuition was trained in a narrow band of conditions, and when we leave that band, matter becomes newly inventive. The liquid that climbs walls is not an exception to the universe. It is part of the universe, operating in a region our bodies were never meant to experience directly. There is also a practical side to all this. Superfluid helium has been essential in low-temperature research. It has helped cool instruments and materials, supporting the study of superconductors, quantum systems, and precision measurements. Its unusual heat-carrying ability makes it useful in specialized cooling situations. More broadly, the physics of superfluidity has influenced the development of quantum technologies and our understanding of coherent matter. Even when a phenomenon seems remote from everyday life, the concepts it reveals can become part of the foundation for future tools. Science often works that way. A strange liquid in a low-temperature laboratory may not look practical at first. Later, the ideas learned from it help shape technologies that depend on controlling quantum states with extraordinary care. Still, the deepest value of superfluidity may not be technological. It may be conceptual. Superfluids change what we think matter can do. They show that a liquid is not defined only by its ability to pour. They show that friction is not inevitable in all forms of motion. They show that rotation can be quantized. They show that many particles can enter a shared state and behave as one system. They show that extreme conditions can make the hidden rules of nature visible. That is a great deal for a substance best known outside the laboratory, for lifting balloons and making voices sound briefly ridiculous. There is a gentle lesson in helium itself. It is simple, quiet, and chemically reserved. It does not bond eagerly. It does not burn. It does not behave like a dramatic element in ordinary life. Yet when cooled near the bottom of the temperature scale, it becomes a doorway into some of the most profound ideas in physics. This is a useful reminder that strangeness does not always come from complexity. Sometimes the simplest things, placed under the right conditions, reveal the deeper structure. Helium does not need elaborate chemistry to be extraordinary. It only needs cold enough silence for its quantum nature to be heard. The word silence fits here in a practical sense, not as decoration. Thermal motion is noise. Not sound noise exactly, but physical disorder, random motion, constant agitation. Deep cooling quiets that noise. In the quiet, coherence can appear. This is true not only for superfluid helium, but for many low-temperature quantum systems. To build and study delicate quantum states, scientists often need to isolate them from disturbance. They cool, shield, trap and control. The less the environment interrupts, the more the quantum behavior can persist. Superfluidity is one of the classic examples of what can happen when the noise is low enough and the particles are able to cooperate. That cooperation is not planned, not guided by intention, and not directed from outside. It emerges from the rules. This is one of the most humbling things superfluids reveal about the universe. Order does not always require a designer in the ordinary mechanical sense. It can arise from simple laws acting on many particles under the right conditions. The atoms do not know they are making a superfluid. They do not know they are climbing a wall or forming vortices. They simply obey quantum mechanics. From that obedience, astonishing collective behavior appears, and yet the behavior is not remote from us. Every time we talk about superfluidity, we're also talking about the limits of human intuition. We learn that our common sense is not wrong, but local. It works beautifully for warm liquids, falling objects, kitchen spills, and the 1,000 practical tasks of daily life. It does not automatically extend to helium near absolute zero, or to the inside of a neutron star, or to electrons in a superconductor. Science does not replace common sense by mocking it. Science shows where common sense works, where it stops, and what deeper patterns take over. That can be a calming thought. The universe is not obligated to be familiar, but it is understandable. Not always quickly, not always easily, but patiently, with experiments, models, and better questions. Even a liquid that climbs walls becomes part of a coherent story. The first observation may feel impossible, then the pieces begin to gather. Extreme cold reduces thermal motion. Helium remains liquid because of its quantum nature. Its atoms can enter a shared state. The superfluid component flows without ordinary viscosity. Thin films can carry that flow along surfaces. Rotation appears through quantized vortices. Each step makes the impossible less impossible without making it ordinary. That is the best kind of explanation. It does not drain the wonder away. It makes the wonder more precise. A vague miracle becomes a real phenomenon. A trick becomes a doorway. Superfluidity remains strange after we understand it, but it becomes strange in a way that can be measured, predicted, and connected to other parts of physics. The liquid climbing the wall is still delightful. It is simply no longer alone. It belongs to a larger map of quantum matter. As we come back to the image that began the journey, the small vessel of helium feels different now. At first, it was a curiosity, a liquid that climbs walls, a substance that refuses to stay put. Now it is a summary of deep principles. In that climbing film are the ideas of surface flow, quantum coherence, low temperature order, and the absence of ordinary viscosity. In the persistent current is the idea that motion need not always fade by familiar means. In the vortex is the idea that even rotation can be broken into quantum units. In the superfluid state is the broader message that the universe permits forms of matter far outside the range of ordinary experience. So what do superfluids reveal about the universe? They reveal that matter is more flexible than it looks. They reveal that the rules of the very small can organize the behavior of the visible world. They reveal that resistance, disorder, and friction are not always built into motion, but arise from particular conditions. They reveal that a group of simple particles can become a whole with new properties. They reveal that the cold is not merely a place where things stop, but sometimes a place where hidden forms of motion become possible. They reveal that the same principles can link a laboratory liquid to the dense interior of a star. And perhaps most importantly, they reveal that reality is not limited by what seems reasonable at room temperature. That last point may be the one worth carrying into the quiet. Room temperature reality is only one chapter of matter, though we do not need to call it that out loud. It is the version we can touch safely. It is where water pours, cups behave, and friction makes motion settle. But far below that familiar range, helium becomes a reminder that the universe has other manners. It can be smooth beyond smoothness, ordered without becoming solid, mobile without ordinary drag, and strange without being lawless. The liquid climbs the wall not because physics has failed, but because physics is richer than the habits we learned from warmer things. And now, wherever you are listening from, perhaps there is some ordinary liquid nearby. Water in a glass, tea in a mug, rain moving down a window. These liquids will not climb out in a superfluid film. They will not form quantized vortices in the same way. They will behave in the familiar manner, which is probably best for furniture. But behind their familiarity is the same universe that allows helium in the deep cold to become something extraordinary. The ordinary and the impossible are not separate worlds. They are different conditions of the same physical reality. If this quiet journey through superfluidity has helped you settle, or simply given your thoughts somewhere calm to wander, I would be grateful if you liked the video and subscribed. It helps this gentle corner of science reach others who might enjoy learning about strange matter while the room grows still. And as you drift on from here, remember that even the simplest things may hold hidden depths. A liquid can be more than a liquid. Cold can be more than stillness. Motion can continue when friction has no easy way to catch it. Somewhere near the lowest temperatures we can create, helium keeps teaching us that the universe is not only vast above us, in stars and galaxies, but also vast within matter itself, waiting quietly in the places where ordinary experience grows thin.